Close your eyes. What do you see? Do you see yourself? The path in front of you? The next step? Do you see your ambition? The cutting-edge approach that opens new dimensions in medicine? The biggest miniaturization that lays the foundation for the digital revolution? The holistic perspective that transforms humanity for good? The progressive vision that changes everything? The way you see the world, the way you capture moments, the way you transcend knowledge, the way you define precision and productivity, the way you live, move, love, heal, think, are. Open your eyes. Can you see it? Together, we are challenging the limits of imagination. For those who see beyond. Zeiss. Seeing beyond.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMECA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMECA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMECA is part of the Materials Analysis Division of Amatec, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMECA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMECA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMECA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMECA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMICA, Science and Metrology Solutions.
Atom probe tomography. It's the only material analysis technique that offers both 3D imaging and composition measurements at the atomic scale. And it's contributed to significant advances in science. Here's how it works. The solid material being studied is prepared in the shape of a needle with an end radius between 50 and 100 nanometers. That's 10,000 times smaller than the width of a human hair. The needle is frozen at a temperature colder than the dark side of the moon to hold the atoms in place and is biased at high voltage, between 1 to 15 kilovolts. As a result, the sharpness of the tip and the high voltage induce an electrostatic field at tens of volts per nanometer, right at the tip's surface. Then, through laser or high voltage pulsing, one atom at a time is removed from the surface by field evaporation and projected onto a position-sensitive time-of-flight detector. Here's what that does. It allows you to simultaneously measure 1. The XYZ positions of the ion impact, and 2. The atom's time of flight, which can identify the element. Together, these pieces allow you to create a 3D reconstruction of your sample with up to 80% detection efficiency. Put plainly, APT gathers valuable data that's otherwise hard to obtain, providing information that other methods can't. Information, for example, that enabled higher efficiency LED light bulbs, significantly reducing electrical consumption worldwide. CAMICA is the exclusive manufacturer of atom probe tomography technology. Our LEAP and ICOS instruments are at the forefront of material science research. Want to learn more? Download our atom probe tomography tutorial, a practical introduction to the APT technique, or have a look at the 2018 Materials Research Society webinar, An Introduction to Atom Probe Tomography and Its Applications.
Hello, everyone. Welcome to the Functional Materials D session. My name is Tong Li. I'm from Ruhr University Bochum in Germany. So today we will have a series of talks about functional materials, apparently because this was the name of the session. And so for the, because we have a different time zone, I will try to keep the program on time. And I will give the invited speaker 5 minutes notice. Just say this. And for the other speakers, because you have a 15 minutes talk, I will give you 2 minutes notice. Just make sure that we're on time. And for the audience, if you want to ask a question, and feel free to raise your hand after the talk. I mean, of course, this is we see how much the time we left. And if you want to ask the question or interact with the speakers, feel free to write this in the chat. And so I noticed that yesterday some of the speakers had some internet problem, and if I found out we cannot hear this clearly, and I will let you know. I mean, maybe it's better plan to just switch off the video. I think we still have a 4 minutes. Beth, do you want to try to share a screen? I think it should be everything okay.
I can try, yes.
Yeah, and then
can you hear me okay?
Yes, all good.
Good, okay. I mean, the light in the background makes it hard, because if I do this, you think I'm like, you know, God appearing from the skies. I'm no God. Anyway, can you see the slides now?
Yeah, good. Yeah.
And
good.
They are in full screen mode now?
Yes. Yeah,
good.
yeah. I think it's good from my side. Yeah.
Okay, cool.
Yeah. I will because I think the session is starting 3 minutes. I will slowly introduce Baptiste Gout, and I reckon most of you have already know him or interact with him. I mean, over the years, and I think it's always good to make it a bit of officially to have a full introduction of the invited speaker. So Baptiste received his PhD degree with François Bapio. Hopefully this pronunciation is all right. I mean, from University of Bonn, and his topic about new generation of pulse laser atom probe. And this is one of a very important topic, as we know. And because of this, Baptiste received a very important, prestigious award from DFG in 2020. This is called Leibniz Prize. Leibniz Prize, and this is shows the important contribution to the field. And Baptiste has been basically in different labs across the world, and he was in APT&M at University of Sydney, and he got a Marie Curie Fellowship at University of Oxford, and he also have a short-term assistant professorship at McMaster University. But now he's a full professor at Imperial College. At the same time, I mean, his main role is the group leader at Max Planck Institute for Eisenforschung, and this is in Düsseldorf. As we know, we see a couple of talks. It's basically they're the group members from Baptiste group, and very, very interesting. Baptiste also was Elsevier editor, and he's still now editor of the Materialia, which we know that this is one of the important journals for structural materials and alloys. Yeah, so I think because we have known him so many years, I think his contribution to this reconstruction, understanding the dissociation of complex molecules, and also his pushing, I mean, his efforts to push this cryogenic UH3 transfer solution is really, I mean, some of the group already benefit from that. This means we can analyze the materials in this pristine state, which is super important for most of the functional materials. So recently, Baptiste moved to the battery direction, and this is what his talk going to be about. I think I'm sure everyone is looking forward to this. So I think you can start now, Bat.
Okay, thank you. It's quite humbling, but anyway, yeah, I mean, we are trying to contribute our share to the development of the cryo efforts across the field, and I think there's a lot more to be harvested in many directions. Anyway, so I will mostly present the work that has been led by Seho Kim, and there's a small group of people now who are working within the larger group on batteries and more generally energy materials under the co-leadership of Seho Kim and Rhett, whom you may have heard talk yesterday. So there's also going to briefly talk about some of the work that Xiam is pushing in the neighboring theory department, jointly with Christophe. You might also have heard Christophe ask some questions yesterday. There are a couple of posters that are really worth looking at on their push towards theory of field evaporation. And some of that work is also on the experimental side is joined with colleagues in Berlin, especially Kong and who's in the group of Ingo Manke. So for just a little bit of context, there's a huge demand for batteries across the world for phones and cars and almost everything, grid scale storage that we might need to store renewable energy generated by renewables. So there's these massive plans worldwide. There's plants that are being made everywhere. The battery demand might be, multiplied by almost 20 compared to a few years ago, and this is just even in Europe. There's a huge increase in the demand, but also in the supplies, and there are plants being made everywhere. And naively, when I started thinking about these things a few years ago, for me, a battery is just this electrochemical device with an anode, a cathode, and then in one way we either power a device, or in the other way we're just recharging. But what I tended to forget is that it's actually made of materials like everything else, and so as such it has secondary phase that can be on both sides, in both electrodes, boundaries, grains, cracks, dislocations, defects, the types of things that I am more used to, at least from more the metallurgical side of studies, grains, but also in the electrolyte itself. When it's liquid, we can have species that actually come from the corrosion of the electrodes. We can have fragments or things that are actually floating in there. The evolution of the electrolyte composition can also change over the course of the cycling. And then there's these different interfaces that are forming at the interface between the electrolyte and the electrodes. And we've heard a bit about this in one of the posters. So it's actually very important to be able to measure the composition and the atomic arrangements inside of the different parts, whether we talk about the cathode, the electrolyte. You've seen maybe the talk yesterday from our colleagues in Aachen. And we need to really understand the details of how atoms are arranged in these different parts of a battery. Are there impurities? What role can they play? And how does this evolve as we cycle this electrochemical device? And how this evolution actually affects the performance, the storage of, for example, lithium on one side and during charge and discharge. So Atom Probe seems well suited to look into battery materials, but I always said no to everyone asking to work with us on this, mostly because when a young bat was working at Sydney 10, 12 years ago, was a colleague, Wai Kong Yao, started to try to run some lithium containing titanium oxides that can be used for anodes in batteries. And although the runs were all quite nice and the peaks in the mass spectrum were what you would expect more or less, and the problem is that the spatial distribution of the lithium was always more or less messy, and we always found a lot of lithium towards the top of the needle and none at the bottom. And you could do this again and again and again very repeatedly. The lithium distribution didn't seem to be what it should have been, and it seemed to be affected by the run itself, the experimental, performing the Atom Probe experiment itself. And many other people started to look into this and had faced the same types of problems. So a few years afterwards, there's this paper from the Stuttgart group, and they had a slightly different sample configuration where they had a support shaped as a needle, and then they deposited glass on top, and then depending on the type of glass, they also saw lithium basically being pushed out, and they proposed a mechanism whereby the field, the electric field itself that we are generating, and especially in this configuration where we have a sharp needle and a glass on top, the fields through the glass can actually drive the lithium out. it's electron migration. This is how a battery works. So that sort of makes sense. In the more now conventional geometry for samples, where we have a support on which we apply the electrostatic potential and this lithium containing material on top, in principle, we would expect that the field is the highest where the radius is the smallest, so right at the top there. But same thing, there were a few attempts at using these types of configurations in the hope that the field would not actually affect the distribution of lithium so much. But actually, in whatever report, we can find multiple reports of lithium losses. Again, diffusion of lithium forming hotspots on the detector. And this, even though this was done at a higher base temperature, the problems were also faced at lower temperature. There's still a few scattered results here and there. So from the group in Göttingen, for example, from Arun and in the group at PNNL, from folks from South Korea at Samsung, they really seem to show that, I mean, in there, they actually removed the lithium and just looked at what was left behind after the lithium had gone out. But here we can see lithium inside, and we just couldn't really understand why in some cases it would work and what we were doing wrong when we were trying. So the first thing that came to mind was that maybe the specimen preparation itself was causing problems, or maybe it's something happening during the analysis. I think, as I said, there might be issues related to the field. And because we were sort of pushing this cryo atom probe, the first thing we thought was that if it's related to the specimen preparation, actually redistributing the lithium because of damage from the Fib or interactions with the gallium in particular, we wanted to use our setup at MPIE that has a couple of atom probes of LEAPs connected to a glove box and to 2 cryofibs, one being just commissioned this week, and all of this connected by this cryo UHV transfer suitcases. So we can take samples from the glove box into the Fib, make needles, go into the atom probe, and vice versa. And typically we can do, so this is a typical specimen preparation with the Fib. This can be done only at room temperature for now. We're not conversely to what they're doing at PNNL, for example, where they can do the full cryo lift out. We do lift out at room temperature, which for these materials is typically fine. And then afterwards we can do the sharpening at cryo temperature, for example. So we took, for example, pure sodium in our glove box, stuck it onto a puck, transferred it through the suitcase into the Fib, made a needle, then transferred this into the atom probe afterwards. It's the same types of protocol we use for water, for example. In this case, we actually didn't do a lift out. We just dug a hole all around with the plasma Fib and left a small pillar in the center, this sort of moat approach that was discussed yesterday, for example, by colleagues at Zeiss. And here you can see the light. You can see the needle made of ice, and we could actually transfer this into the atom probe, locate it inside of the atom probe, place it in front of the local electrode, and then run this. So we wanted to do the same for battery. So we got some nickel, manganese, cobalt 811 powder, commercial powder from colleagues at Imperial College, and made cryo needles, and we're super, hopeful. And the runs were all shit. Pardon my French, maybe, but they were all very bad. We had all of this dilithiation, like big blobs of lithium coming out, and very difficult to control field evaporation conditions. After we played a lot with the parameters, we ended up in a situation where at about 60K and fairly low laser pulse energy on our LEAP 5000 XS machine, we could get distributions that were less messy, let's put it this way, but still we could see some degree of lithium migration towards the surface. So I would consider this as a fail. And when we think about the geometry of the specimen, we would expect that there's enough of a surface conductivity even on samples that are not very good electroconductor, maybe because of defects, surface defects, because of surface contamination, and then the bending taking place when we start applying the high field. So this, in principle, the surface conductivity should allow for the field to be generated right at the top of the needle, and normally to be shielded within a very thin layer. So in principle, there's really very little reason to have delithiation taking place. But actually, if you think about it, if this layer is not ultra thin or smaller, thinner than an interatomic distance, then the field probably expresses itself sufficiently inside of the sample, and it can drive just a little bit of lithium migration right from this region. But then you establish a gradient of lithium between the core and the edges of the specimen, and even at 30K or 40 Kelvin, lithium can move out. And this can happen at the top of the needle, on the edges of the needle. There's then a gradient of field, so the lithium can just migrate along the shank and all be detected towards the top. This is basically what seems to be happening, but maybe there's a way to avoid the problem by depositing a layer that is electroconductive on the specimen. And this should prevent the penetration of the charges, except right at the top of the specimen during the field evaporation. And maybe this is the way to actually solve the problem. So Seho, who has been developing these techniques for typically nanoparticles to do electrodeposition of a metallic matrix containing particles of interest, has used the same technique here. So we have a copper substrate, we have a nickel film that has been deposited that contains the particles of interest. And then on top here, we've deposited platinum in the fib, and then did slice and view. You can see this composite there deposited on the copper substrate. So we did this with the same lithium titanium oxide that I tried in 2010. And in this case, instead of having a bulk sample, we just have particles that we bought commercially from Sigma or something. And you see they're all dispersed in the nickel matrix. Good thing is when we do the analysis of these particles individually, the lithium doesn't seem to move. It really is, more or less distributed in the way we would expect. The composition is, as good as you could get it from the atom probe. That seems to be really a good way to go in some ways. But that does not explain the observations from this couple of papers, for example, because in this case, they're not shielding the specimen extrinsically using a metallic layer, and there were still many open questions there. So the difference is beyond the fact that we tried to make samples at cryo temperature, is that we transported the samples through the vacuum suitcase, whereas Aaron and co, they just took the samples from the fib and went into the atom probe walking through air. So we did the same thing. Seho prepared a sample in the fib, made the needle, took it out through air, put it into the atom probe, ran it. And then the sample runs, and the composition is more or less homogeneous all across. It's a bit boring, but at least there's very little issues with respect to the lithium electromigration. So the transport in air seems to play a role. So what we did afterwards was take the sample, stick it in air and back in, and effectively we have found a whole layer of halogenated species on the surface, OH, H2O, OH3. And by trawling through the literature on some of these oxides, it seems that when they get covered with moisture, their surface conductivity changes substantially. And so what we believe is happening is that the sample, by putting it through air, actually gets covered by a layer of halogenated species that changes its conductivity sufficiently to provide some degree of shielding against the penetration of the field. And that actually helps massively and avoids the electron migration of lithium. So this was a good, maybe rabbit hole to get into from an atom probe perspective. But what that did, at least in my mind, was that it's like, okay, so maybe we can look at materials containing lithium or sodium, and maybe we can get into this realm of battery materials. So we started looking at other samples, like other NMCs, so nickel, manganese, cobalt oxides. We looked at some silicon anodes, model systems, talk about this afterwards, starting to look at defects in those systems. We could actually freeze the electrolyte after cycling and do some analysis of this. Again, I'll get back to this. We started looking at pure sodium, for example, that is probably somewhere in the future one of the electrodes that will be used. And then we started looking into these interfacial layers that develop, in this case, on a zinc battery, and the deposition of some carbon species coming from the electrolyte. And more. But anyway, today I'm just going to give some details about the work we've been doing on this silicon anode. So again, in principle, silicon could be an extremely good anode material. Typically at the moment in commercial batteries, it's mostly graphite that is being used, but the graphite cannot hold as much lithium ions as silicon could in principle. And there are also issues with the sourcing of the graphite necessary for these batteries. And there's only a couple of plants in the world that are making it, and it's in relatively short supply. The key issue for silicon is that when lithium, when it gets lithiated, you form silicides, and the silicides have a huge volume increase compared to the silicon itself. And as the lithium goes in and out, you actually accumulate defects, and either it's just stress or it's new phases, grain boundaries, and cracks that are forming. So in principle, it's all stuff that, you know, Atom Probe could look at. I mean, cracks not so much, but the rest could be quite interesting to look into. So we summarized all of the results I'm going to show in that paper that was released recently. If you want, ask a copy or something, it's no problem. So we took just a wafer, 111 oriented silicon, something very simple. We have this typical liquid electrolyte. Don't have the composition here, but I can give it to you separately. And then it contains this salt, lithium phosphorus F6. And after a number of cycles of lithiation and delithiation in CV, so not exactly what would be in normal conditions, but we could see that there's a loss in the amount of lithium that gets captured by the electrode. There's less and less and less lithium actually being incorporated and then released. So we are losing capacity from the first cycle down to the 25th cycle. It's really quite quick, actually. And after different times during cycling, we stopped, and then we took the sample and did some atom probe analysis. So it took the electrode, it's here, it did this inside of the glove box, stuck it onto a clip holder, then plunge freeze this in liquid nitrogen, took it into the fib, and in the fib made samples, and then went into the atom probe. So this is a typical sample. You can see here the modes that was made, the pillar, the needle. First needle was actually prepared right within the frozen electrolyte. We find a number of silicon ions spread across a whole zoo of carbon, oxygen, halogen species, as you would expect from the analysis of organics. There were hints in previous papers that the residual moisture from when the cell, the battery was made, could actually cause the dissociation of the lithium salt here that might generate HF that then in turn actually causes damage to the silicon electrode. And so what we are seeing in these with these ions that are floating around inside of the electrolyte are actually coming from the electrode itself. So we did an analysis of the electrolyte not on silicon, and we could actually already see that there was no silicon inside. So here we could really prove that already by just even before you cycle, by putting the electrolyte on top of the silicon, the residual moisture can already cause some degradation of the surface of the electrode itself. And then after we stopped the run, it was resharpened, and the specimen was run inside of the silicon. And in this case, you know, this is before cycling. We just find silicon as you would expect. You know, it's typical 111 planes, or I mean, they're collapsed 444 planes, I think, and the typical threefold symmetry that you would expect from this set of planes. And then after one cycle, we did this again. So inside of the electrolyte, we found a silicon-rich region, like a small block of silicon. It's a pull that actually comes from the electrode itself. After the first cycle, we have this small nanoscale fragment inside of the electrolyte. And inside of the electrolyte, we also find more isolated silicon ions, so the corrosion kept going on. And this fragment, we could see that it's actually silicon in the core, and a whole lot of silicon and oxygen species all around on the surface. So we could try to quantify some aspects of this. We could find 2 of those fragments in this one data set. There are a few others scattered around. So the problem with these fragments is that, so first, they are really products from the electrode itself. So it's really the degradation of the electrode, but also they can go into the electrolyte. There's normally a separator between the two, which is like small series of small pores, and it can just go and block some of the pores. So it can actually affect the capacity also of the battery itself. And then after 25 cycles, so towards the end of this cycling that we did, we could actually see grain boundaries inside of the silicon data set. There's some silicon and oxygen species on the surface, so SiO peaks, SiO2 peaks, Si2O peaks that are forming small islands on the surface. So this could be some remains from the SEI that was forming during the cycling. And then we could see a whole lot of grain boundaries in there and small grains that formed. Inside of the boundary, we could see phosphorus, and phosphorus again comes from the dissociation of the salt, the lithium salt that we had in the electrolyte. And inside of the silicon, we could see lithium ions, individual lithium ions, not at the boundaries, but inside of the grains. So again, the 111 single crystal progressively becomes a polycrystal. Even when we don't remove entire chunks of the surface, we still damage the electrode underneath. We have this phosphorus segregation to the boundary, which actually is probably not helping with the cohesion of the boundaries. And we find some lithium trapped inside of the silicon. There might be some remaining vacancies that trap the lithium. There are some theoretical studies showing some highly positive interactions between, energetically favorable interactions between vacancies and lithium. So just to summarize, as soon as we put the electrolyte in contact with the silicon, there's actually some dissociation of the salt that triggers the formation of HF, that in turn actually removes the protective silicon dioxide and starts to cause the corrosion of the electrode itself. As we cycle, we have this formation of lithiated silicides. The volume change actually imposes a huge amount of stress onto the underlying lattice, and this causes amorphization. This has been shown in the past through indentation of silicon, that under the pressure, the silicon starts to amorphize. And then when the lithium is removed, there's recrystallization. So we form a set of nanocrystals inside of the, just on the top surface of the electrode. And so we have nucleation of a whole zoo of small nanocrystals, and we have indications from the atom probe crystallography analysis that these grains are completely randomly oriented when we look at the pole figure. And then we have these pulverized particles inside of the electrolyte, a whole lot of silicon ions, individual silicon ions isolated. And so again, these can be active surfaces. They can actually also contribute to the degradation of the electrolyte itself. And we have these new grain boundaries in which we find phosphorus, for example, that might make these grain boundaries weaker and more facile crack propagation as soon as the next round of lithiation takes place. All of this, goes down to what Atom Probe really is good at, measuring local compositions at different interfaces, defects, and try to understand the mechanisms whereby these electrodes degrade. I think will require these types of insights. And without this, I think for now, people tend to just try quite a lot of different possibilities. But I think the Atom Probe can really shed some light onto some specific mechanisms that are at play, and then we can maybe target strategies to make silicon behave a bit better. So for now, I've shown results that were a bit crap and some results that were okay. There are a number of challenges remaining. I guess I have 5 minutes left, right? Is that it? Yeah, okay, good. Then I should be fine. So again, to get back to this electromigration question, we tried to run some pure lithium. So again, put pure lithium in the glove box, transfer it through the suitcase into the fib, made lift outs, deposited this, did cryo sharpening, transfer back into the atom probe, and then run this under a zoo of different conditions in voltage pulsing, laser pulsing. And more or less what we get are always this sort of really shitty evaporation, hotspots of evaporation. And so the mass spectrometry aspect is fine, but the spatial resolution seems to be completely lost. So it's really hard to control the field evaporation of pure lithium. This was also reported by, I mean, the mass spectrometry aspect was reported, for example, in other papers. I think the group from Stuttgart published on this last year. And so we also tried some other low melting point metals. For example, in this case, it's gallium or pure gallium or an eutectic indium gallium alloy. Same thing. We just put it on a copper clip, plunge froze it, went into the fib, made a needle, and actually we could run gallium or indium gallium. It does run, and we published on this last week. But the thing is, if you try to run this in voltage mode, you get beautiful gallium peaks and it tends to run well. But in laser mode, we get nothing. Like we get zero peak. It's just an absolute mess. So how did we go from this to that? We actually started optimizing the pulsing conditions. So go from a higher temperature down to about 30 Kelvin. And you can see that there's a really massive evolution of the detector map in a way that as soon as you go from maybe about 60 Kelvin, you start to see these hotspots forming. And at about 100K, basically I've lost all like the pole figure that we can see at 30K is completely lost. And you start to form these hotspots everywhere. I mean, gallium is used for these liquid metal ion sources for a reason, right? It is because it gets liquid at fairly low temperature, and then the field actually activates this quite a lot. So I think we need to remain at low temperature, and we need to also use voltage pulsing for a lot of these analyses. But it might not be all. There might also be some physical limits that we are finding. So in this case, we could actually run this and get really good results, good data, seeing phase separation between gallium and indium, and it seems to be working fine. So this is where we started to work with our colleagues from the theory department. So Shyam actually started simulating with density functional theory a slab of pure lithium and looking at the way these two layers, so you have this top layer, bottom layer at atoms, and then look at the simulation as a function of the field of the energy barrier for field evaporation, and also potentially the possibility that atom starts to migrate, because the surface diffusion barrier will also be field dependent. And as you start increasing the field, actually there are many paths, energetically favorable paths, where the atom, instead of field evaporating directly, will start to roll and go onto another position on the surface. And this happens at fields that are lower than the field that you would need to cause the field evaporation. So you're basically dropping the barrier, the energy barrier for surface diffusion before you field evaporate, making it extremely likely that lithium will just move around before going away from the surface. So it might be that we are maybe reaching a physical limit as to what we can really analyze. There might be tricks and ways to play with this, but it seems to be more difficult than we initially thought. So that's me from a few weeks ago. I've aged. I'm wiser now. I think we can run battery materials. I think there's these developments just on the atom probe itself, but also the cryo-atom probe, I think can really complement a lot of the techniques that are conventionally used for battery analysis, like XPS and SIMS and TEM. We can really maybe help understand better this corrosion degradation behavior of electrodes and maybe even the electrolyte. But there's still some fairly complex physics that underpins atom probe, and many things will probably remain hard, and we need to be quite careful when we interpret the results. So yeah, that's it for me. I want to thank all of the people who've been helping, contributing, and the people who are giving us money, the Max Planck Society and MPIE in particular, the ERC that funded a number of people who are contributing to the work. Same thing for the Humboldt Foundation. The DFG with the award of the Leibniz actually made my life easier, so we can actually push these things a bit faster than we would have otherwise. So thanks a lot for your attention, and I guess I can take some questions.
Yeah, but I think you are exactly at the 30 minutes, and I see we have a raising hands. And how about say Richard? I think you are first, and you have a quick one. And
Yeah,
Aaron, do you think you can write in the chat?
Sorry?
And you can start, yeah.
Can you hear me? Yes.
Yes,
I can.
Okay,
yeah.
Look, this is a comment rather than anything else. Electromigration is a process whereby electrons hit atoms. So electromigration would probably cause lithium atoms to move away from the tip. What you've got, as you said at the end, is actually field-enhanced diffusion.
Mm-hmm.
So it's just a question of language, so you don't confuse those outside the subject area.
Okay.
And incidentally, there's an awful lot of theory about this sort of thing in the vacuum breakdown literature, due to the sort of growth in nanoprotrusions.
Yep, we started interacting with people who do this, and yes, there's a lot of literature. Yes, I agree. Electromigration is a term that is actually also used by people looking at lithium-containing glasses for. So we use the term that we found in the literature being used also for diffusion, electromigration through the layer that contains lithium.
Yeah. So
it's not just us misquoting a term. It's maybe another bunch of other people from other communities misusing the word.
Yeah.
More than likely.
So, sounds good. Yeah. Thank you for raising this point. I think we can jump into the next speaker, and Pat, you can answer the question in the chat as well. And so next speaker is Sharon Sheeter, and from AMAC, and I think you can start sharing screen. Good, then you can start. Yeah. Ready to go. Yeah.
Okay, thank you, Professor Lee, for the introduction. And I'm very glad here to have the opportunity here today to talk to you about our atom probe tomography study on nickel aluminum thin films. Okay, so for the motivation of our work, I would like to start here with a cross-section of a commercially available integrated circuit, where here on the bottom you see these finger-like structures, which are the actual transistors. But for the integrated circuit to function, they need to be electrically connected. This happens through the so-called interconnects. And it appears that currently we are hitting the limits of the materials currently used as interconnects, more specifically copper. So when we shrink down the copper interconnect, the copper resistivity is increasing up to the point they can no longer be implemented in future interconnect devices. And that's of course what we want if we want to keep up with Moore's law. So that's why there is a search for alternative solutions to this, and the nickel aluminum alloy has been proposed as a very interesting candidate for us due to its low bulk resistivity, but also due to a host of other properties. Now, we are not just interested in any nickel aluminum alloy. We want a specific phase, namely an intermetallic phase, which nickel aluminum portrays at the stoichiometric composition of 50 atomic percent. To understand what that is, we can first have a look at a random alloy, and in a random alloy, the atomic species sit at random lattice site in the crystal lattice, which perturbs the periodic potential, and this disorder increases the resistivity of the material and increases the electron scattering. However, some materials like nickel aluminum have a so-called intermetallic phase in which the atomic species are ordered in the lattice, and this order reduces the electron scattering and hence increases the conductivity. So here we see, for instance, the resistivity of nickel aluminum as function of the composition, and at stoichiometric nickel aluminum at 50 atomic percent, the resistivity has a clear minimum, and it's known that this is the so-called beta phase, so where the nickel and aluminum occupy cubic sublattices which are shifted with respect to each other, and it's exactly this low resistivity phase we want to investigate for interconnect applications. Of course, we then have to produce them using CMOS compatible techniques. So here we have data from PVD deposited nickel aluminum films. So the resistivity as function of the nickel concentration. And we see that indeed at 50 atomic percent, this shows a minimum in resistivity. And upon annealing of these films, this overall behavior is retained, but the resistivity is decreasing. Nevertheless, we still quantitatively do not fully understand all the details of this behavior. For instance, why we are still quite far off from the desired nickel aluminum bulk resistivity. And that's why we resorted to advanced characterization techniques like atom probe tomography to try and find some more puzzle pieces to complete this puzzle. So this is a cross-section of the sample. In this talk, I will talk about nominally stoichromatic nickel aluminum samples right after the deposition and after post-deposition annealing. From samples we analyzed in our LEAP 5000, and here you see an example of a reconstruction where the reconstruction parameters were guided by the nominal thickness of the nickel aluminum layer. So let's have a look at the data. So here I show a slice of the data from the non-annealed sample, and we can immediately see that the aluminum and nickel point cloud density is not uniform, which is then also visualized if you use the nickel, for instance, a nickel density heat map. Now, what we find is that these variations are quite clearly correlated to field variations, through which we see through the charge-state ratio distribution, which is also non-uniform, which suggests that during the field evaporation, locally over the apex, the field was non-uniform. What we can already see, maybe a bit by eye, is that these are correlated. So high charge-state ratio regions correspond to low density and vice versa. So if we pixel per pixel put this in a kind of correlation plot, we see that the nickel charge-state ratio is correlated with the nickel density quite strongly. On the bottom, I will now show this exactly the same analysis for the post-deposition annealed sample, where again we find a non-uniform nickel density and non-uniform nickel charge-state ratio distribution, which are again correlated with respect to each other. But we see that upon annealing, the details and the morphology seems to change. So how do we explain this? Well, this is due to the polycrystalline nature of these films. So here we have a complementary TEM analysis of a comparable nickel aluminum sample, where we see that this is indeed a polycrystalline film with a grain size of about 10 nanometer. Upon annealing, we know from TEM the grain size grows, and the typical sizes of the feature we see in the point cloud density indeed also follows this trend. So what we think is happening is that the different structural features in this polycrystalline film, so let's say the grains and the grain boundaries, have a different evaporation field, which makes that during the field evaporation experiment, there is a formation of a local curvature across the tip, which leads to local magnification effects, which we then see as these unphysical density variations. And we also get local field variations due to the different tip curvature. Here at IMEC, we have a unique approach to characterize the topography and the local curvature of atom probe emitters. And tomorrow, my colleague and postdoc, Dr. Johan Tu, will give an update on developments in this area, and he will also actually show the experimental determination of the surface of these type of samples. For the remainder of my talk, I want to focus on perhaps the most striking or unexpected observation we made in these samples, and that is about the composition and the local composition. So on average, for the whole film, we find that the composition we obtain with atom probe is actually quite close to what we expect, namely roughly 50 atomic percent for stoichiometric nickel aluminum. However, as you can see here, for instance, for the non-annealed sample, with some concentration profiles, we see that on the local scale, the composition quite drastically varies from this average level. We can also visualize this in 3D. So here you see the same slice as I showed before, but now using isosurfaces, we see domains which are either nickel or aluminum rich based on a criterion of the concentration being higher than 55 atomic percent. Upon annealing, it looks as follows. So again, we find an average composition which is very close to the intended stoichiometry, but still on the nanoscale, we see quite severe deviations from this average. And also, again, we can visualize that in 3D. Now, upon annealing, it seems like the films become more homogeneous in terms of composition. For instance, the volume fraction of these enriched regions decreases upon annealing. But first of all, we have to try and determine whether this is not just some APT artifact we are overinterpreting here before we can really reflect upon what this would mean for the properties of the material. Why do I say that? Well, it is quite well known that in atom probe we can obtain the apparent composition of materials which might depend on the conditions you use to run the experiment, and it might be quite off from reality. So for that, I show here an example from my colleague on gallium nitride, where the red data points show that depending on the conditions you use, and we believe that the field which we can capture through the charge state ratio is the best way to capture this, seem quite strongly correlated, and you can get results quite off from reality. Now, what is also known is that this is also valid on the local scale. So if you somehow have local field variations across your apex, and for gallium nitride, we have this, for instance, because of the crystallography. So we have poles and zone lines corresponding to high field and low field regions. And also here, if we inspect the local composition, there seems to be a correlation with the local charge state ratio. So I've already shown you that we have these local field variations as well in our samples, and we might ask the question, well, is this not just the reason why we see these composition fluctuations, and hence are we here overinterpreting some kind of artifact? In order to assess that, we have done the same exercise as here, basically. So we have here the average atomic composition for a number of experiments done at different APEC fields. It was varied for more than 2 orders of magnitude, actually. And then we see that the overall variation, taking everything into account, is about 3 atomic percent. And if we compare that then to the fluctuations we found in a sample, we see that these fluctuations are much, much more. So that should suggest that if there is an eventual compositional bias in these samples, it seems to be much less than the composition fluctuations we want to investigate. We can also try to investigate that on a local scale, for instance, by again trying to see if there's any correlation between the composition and the charge state ratio, or do this using line profiles. But also here, we do not find any clear correlation locally between the composition and charge state ratio. So I think we can conclude that what we see here in terms of this local off stoichiometry, we cannot attribute that to any artifact. So for the final slide, I would like to reflect about what the significance of this observation is for the properties of this film. So here I repeat some snapshots of this local off stoichiometry. And of course, we can ask ourselves the questions, well, is this now actually close to what we are aiming for, like this beta nickel aluminum phase? Because to be honest, it looks quite messy in a way. Luckily, we have a complementary characterization, for instance, grazing incidence XRD, which shows us that the crystallites in the sample are indeed from the beta nickel aluminum phase. So to consolidate now we can have a look at the phase diagram of nickel aluminum. And actually, the beta nickel aluminum has a quite broad phase field, meaning that between nickel compositions of about 45 to 60 atomic percent, the beta nickel aluminum phase can persist. However, for the aluminum-rich side of this phase field, we get nickel vacancies in the nickel lattice, and for the nickel-rich side, we get substitutional nickel in the aluminum lattice. These defects, of course, have an influence on the electronic transport because they act as point scatterers. Now, what we now learn from atom probe tomography is that despite the average composition being close to stoichiometry, the more of stoichiometric you are locally, the more of these point defects you have, and hence we have more of these point defects to be taken into account than initially expected. For For the people who've already looked a bit more closely at my slide, perhaps also notice that we also detect locally compositions which are even beyond this phase field, and it might be that there is some nucleation of neighboring phases or even some random alloy locally in our sample, which means that also things like alloy scattering or perhaps even percolation is something we need to take into account to explain the resistivity of our films. So in conclusion, we have investigated stoichiometric nickel aluminum for interconnect applications. And atom probe tomography brings some new insights here. So before we had the usual suspects like grain boundary scattering in trying to explain the resistivity of our films. But unfortunately, that did not give a satisfactory picture. But the non-local composition fluctuations, as evidenced by atom probe tomography, seem to give some new leads on how to explain this. And that is, of course, also where we're working on. So we want to, in a more quantitative fashion, build this resistivity model. And we are also analyzing nominally off stoichiometric samples to complete this picture. I would like to finish with the acknowledgements. So Arthur, an intern with us who helped in acquiring part of the data, the IMEC Interconnect and TEM teams, and funding from the Flemish government for the used infrastructure for this work at the University of Leuven. And with that, I would like to thank you for attending my talk. And also, I hope next year we see each other again face-to-face in the next edition of the APT&M here with us in Leuven. Thank you.
Yes, thank you. I think we were 2 minutes shift, and so we have 1 minute for questions. So I want to mention that, I also analyze this thin film nanocrystalline and iridium, and I see there's a density variation, and you have this super nano, like a 4 or 5 nanocrystals. So essentially, when I see your data, I feel like this is definitely a bit of a spin-off decomposition. You call this decomposition fluctuation, and combined is a little bit maybe Grimonder segregation. But specifically, I don't know how the sputter process really allow this segregation takes place, but this is a kind of a, because you see both nickel rich region, aluminium rich region, this is something both can take place, which is rather complicated.
Yeah.
Yeah. Okay, good.
So, right. Yeah.
Yeah. Okay, good. Thanks for the great talk. And let's, like you said, we hope to see each other next year in Belgium. And so our next speaker is Yunhong Li, and she's from Stuttgart University. And I think you can start sharing your screen and start your talk.
Yeah. Can you see my screen? And
oh, good. Yeah.
Can you hear my?
Good.
It's okay.
Yes.
Yeah. Okay.
Yeah.
So hello everyone, it's my pleasure to present my work today, and my work is mainly focused on the characterizing the degree of oxidation on platinum palladium and the platinum palladium alloy system during anode oxidations. So actually my work is based on the after treatment system like diesel oxidation catalyst in a car, and in this system, the platinum and palladium nanoparticles are used as a catalyst to purify the emission gases into the normal gas. And here I want to start with the question of what is a catalyst. So from the definition, the catalyst is a substance which can increase the reaction rate, and after the reaction, it shouldn't be consumed and shouldn't be changed. And I want to highlight today here the unchanged, because this is not always true. So here I want to show you one representative example, which is showing the catalyst is changed during the reaction. So this is the anode conversion measurement by flatbed reactor. So on the right side images, you can see the flatbed reactor instrument. And this work is done by my colleagues, Daniel and Ute, and they firstly produce the nanoparticles and deposit these particles in the gas filter. And this sample is placed in the reactors. Then they apply the anode gas mixtures and starting the alternative temperature ramp, and they measure how much of anode gas is oxidized to the NO2 gases. And here I want to remark, in this talk, I always talk about first the heating, cooling, and so on. So always the heating cycle is presented with A, and the cooling ramp is presented with B. And let's move on to the left side. Here you can see the anode conversion result for the platinum. And especially platinum shows the inverse hysteresis, which means during the heating cycle, the conversion rate is higher than the cooling cycles. And this is because the catalyst itself is oxidized, as you can see here. So it's very important to figure out the oxidation behavior of the catalyst because it has a directly effect on the performance of the catalytic converter. That's why the noble metal oxidation has been intensively studied with the various characterization methods. So a lot of work has done with the diffraction and the spectroscopy and microscopy method to analyzing the catalyst surface, especially during the anode conversion. But however, the most of samples are prepared in a bulk or in the thin film structure, and the measurements were conducted in an ambient condition, which can induce the unpredictable contaminations. So yeah, it's true. It's really tough task to characterizing the individual catalyst because the catalyst is really small. And as you can see in the TM images, the size of catalyst is tens of nanometer or even smaller than 10 nanometers. And this side, it has the three-dimensional spherical shape. And the oxidation normally happens at the very topmost surfaces, which means we really need the highly delicate the analysis technique, which has in atomic resolutions. So here I can say the atom probe tomography is a very suitable characterization method to see the oxidation behavior on the individual catalyst. So the goal of this work is the proving the oxidation states of platinum, palladium, and the alloy system during the anode oxidation. And this data is directly compared with the result of the anode conversion measurement. So now let's move on to the experimental procedure. So for this work, I used the wire samples. And for the platinum, pure platinum and the palladium sample, the tip produced using the electrochemical polishing method with the calcium chloride and the nitric acid solution, respectively. And in this case, in the case of the alloy samples, the focused ion beam technique was used to produce the tip. And here you can see the TM images for the pure palladium tip sample. The size of apex is around 20 nanometer in the diameter, which is a very similar size with the nanoparticle catalyst. And the hemispherical surface can model the surface of the individual catalyst. And these produced tips are inserted into the APT instrument. And now I'm so happy to show our instrument, the custom-made atom probe, especially optimized for the catalyst research. It's because here we have the additional chamber, the named reaction chamber, which is connected to the atom probe in the ultra-high vacuum condition. So all the sample transfer can be conducted in the ultra-high vacuum system. And also this chamber is connecting with the gas supply system and also the control system for the pressure and the temperature. So in this reaction chamber, I can achieve the same conditions of the anode conversion measurements. And after the tip sample was inserted in the APT instrument, then firstly, the tip is filled, evaporated. This is the kind of the pre-cleaning step because normally as produced the tip, it's not perfectly clean and there are always tiny contaminations on the surfaces, which can stem from the preparation step. So in order to remove all the dirties, the further evaporation is done until we can observe only the pure, the metal peaks in the mass spectrum. Then the cleaned sample is transferred to the reaction chamber, and I use the same concentration of gas mixture and the same temperature ramp with the anode conversion measurement. And as I mentioned at the beginning of this talk, the goal of this work is to determine the surface changing during the anode conversion. So for this, I have to freeze in the samples at certain point. So I choose the end point at 100, 200, and 300 as first 3 REMs. So for instance, if I want to get the samples here, the first cooling at 300 degrees Celsius. So when the temperature is reaching to here, this point, then directly apply the cold water circulations to quench the samples. So here the blue curve shows the freezing speed, and it's really enough to fix in the atoms on the surfaces. And the oxidized samples were transferred in the main chamber for the atom probe measurement. And for all measurements, the laser pulse was applied, and the laser wavelength is 355 nanometer, and the repetition frequency is 100 kilohertz, and the average power is the 15 milliwatts. And always the cryostat temperature is set to the 38 Kelvin. And during the evaluating the data, there was a question, how could we evaluate the degree of oxidation to get a reliable comparisons? Because we cannot simply compare the data because the size and the shape of tip, they are very similar but different. So we had an idea to calculating the effective oxide thickness using the atomic density of the metal. And the atomic density is a constant and the known value from the literature. And detection efficiency is an instrumentation factor. And what else we need? The number of oxygen containing atoms. And also we have to know of the area of the apex. So we can get these two values from the atom probe measurement result. So from the 3D reconstruction, we can get the area of the apex. And from the mass spectrum, we can get the number of the oxygen containing atoms. And finally, we come to the results. So here, the direct comparison of the anode conversion and the effective oxide thickness is presented. So on the left side images, you can see the anode conversion shows only one time conversion occurred during the first heating cycle. And then it shows the minimum conversion during the rest of the cycles. And let's move on to the right side images to see the oxide thicknesses. So from 200 to 300 degrees Celsius during the first heating cycle, the thickness is significantly increased. That's why increasing rate in this plot is decreasing here at around 200 degrees Celsius. And further heating and cooling in this, the thickness is increased and keep as a constant value, which means the oxide layer is quite stable and for the subsequent cycles. So here I put the illustration to show the surface state, and take a message from this slide is that palladium shows the only one-time conversion during the first heating cycle due to the very thick and stable oxide layer formation. And here, let me introduce the simulation work. This one done by Dubé. So he calculating the pure metal fraction during the anode conversion. So at the first, the palladium fraction is 1 because the sample is completely clean. And during the first heating cycle, the fraction of palladium is decreased, which means that the palladium is surrounded with the oxygens. And after 300, the fraction goes to 0. That is, the palladium is fully covered with the oxygens. And the fraction doesn't change at all during the rest of the cycles here. So it was very clearly proved the same oxidation behavior of the palladium using the anode conversion and the atom probe and the simulation data. And next one is for the platinum. The platinum has a little bit different conversion behavior to the palladium. So during the first cooling here, the orange curve, first cooling and the second heating cycle, there is a recovery on the conversion. So we call this is the inverse, the hysteresis, and it's really interesting behavior because it only happens in the presence of anode gases. And let's check the atom probe result. So now here I want to highlight in this region during the first cooling, and the second heating cycle, at the lower temperature, the degree of oxidation is clearly decreased. So that means the oxide phase is reduced at the lower temperature. But the oxide thickness is not the same with the initial state. And this also can be seen in the anode conversion as well. The recovery of the conversion is not 100%. And here I also put the simulation data, and it shows the PT fraction is changing during the anode conversion. And let's see during the cooling cycle. So at this point, the fraction of platinum is very small. That means the platinum is already covered with the more oxygens. And for the further cooling and to the lower temperature, the fraction is increased. So it's very clearly proved that platinum oxide is reduced at the lower temperature in the presence of anode gases. So the last one is for the alloy samples. So for the alloy system,
you have 2 minutes.
Yeah, very similar behavior like the anode conversion of the platinum. So during the first cooling and the second heating cycle, there is also the recovery and the conversion. So this recovery was proved by atom probe results. Here in this region, it's very clear the degree of oxidation is clearly decreased. So now we are come to the conclusion. So in this work, the direct measurement of the catalyst surface changing during the anode conversion was possible by using the atom probe tomograph, and the oxidation behavior are clearly proved by the correlative work with the flatbed reactor and the atom probe measurement and the simulation works. So for the palladium, it shows only the one-time conversion due to the very stable and thick oxide layer formation. And for the platinum and the alloy samples, it shows inverse hysteresis due to the reduction of the metal oxide at the lower temperature in the presence of the anode gases. So thank you for your attention, and I also would like to say thank you to my colleagues and welcome to have the questions from your side. Thank you.
Thank you for the very nice talk. And I mean, this is a super cool experimental setup, essentially. And you are talking about this oxide thickness is something like within 1 nanometer regime. And this is based on the calculation of this theoretical value instead of the measuring by the APT, right?
Yeah.
And I'm wondering, like, because the PT and PD is also very effective for anode reduction. And when you do this experiment, did you try to understand, of course, there's the anode conversion, but did you try to see the, say, the residual, the end gases, what is composition of the gases in the chamber? Did you have a way to analyze this?
You mean the remaining gas concentration?
Yes, yes, exactly.
No, so because after the cooling, the freezing the samples, I just evacuating all the gases. So yeah, there is no chance to analyzing the remaining gases. Yeah.
Okay, so you don't know if it's because essentially it can be both oxidation and reduction of the gases takes place. I mean, maybe this is the case.
But in the flatbed reactor measurement from my colleagues, they measured after the reaction how much of the gas they analyzing the concentration of the gases. So yeah, from that they calculate the anode conversions. So
yeah, sounds good. Yeah, we are looking forward for this published work, and we will definitely read it carefully. Yeah, thank you for your very nice talk. And we will jump to the next speaker, who is Joanna Ribeiro from University of Minho, and are you around? And can you please share your screen? Oh, yeah, okay.
Can you hear me?
Yes, good. You can start sharing your screen. Yeah.
Okay.
Good. You can start now.
Okay, thank you. Well, good afternoon, good morning, and probably good evening to some of you. My name is Joana Ribeiro. I'm a PhD student at the University of Minho in Portugal, and I'm presenting an ongoing work of doping impact on the thermal and electrical properties of transparent zinc oxide and titanium dioxide thin films for thermoelectric applications. Okay. This work is part of a collaboration between the University of Minho, where we produce the samples and do most of the characterization, and the Karlsruhe Institute of Technology in Germany, where we do the atom probe tomography measurements and TOFSIMs. Energy is a key part of our life. An estimated 2/3 of all the generated energy in the world is rejected energy, produced and released either via radiation, cooling fluid, exhaust gas, or air. And it's a shame because up to 25% of this wasted energy is, in theory, recoverable, being a big amount actually thermal losses. Thermoelectric-based devices, such as generators, are reliable, durable, and simple to operate. They are able to convert thermal differences into electrical energy and vice versa, making them very promising candidates for this task. In a thermoelectric material, when each junction is at different temperatures, this generates an electric current. This was named the Seebeck effect and is expressed by the Seebeck coefficient, which is the electrical potential applied to the measured in the sample by the absolute temperature applied to the sample. So since none of the existing solutions presents a fully optically transparent thermoelectric, the main objective of my work is to develop a transparent thermoelectric thin film that is inexpensive to produce, non-toxic, durable, and applicable in a variety of thermoelectric devices. These films can be integrated into solar cells, photovoltaic systems, touch displays, or wearable low-power devices in order to render these more sustainable. The thermoelectric figure of merit quantifies the performance of a material, and in order to enhance it, the films must have a high Seebeck coefficient, high electrical conductivity, and low thermal conductivity. Zinc oxide is an interesting choice. It's low cost, relatively low deposition temperature, abundant, and overall non-toxic. Zinc oxide crystallizes in the hexagonal Wurtzit structure and displays an N-type electrical conductivity. On the other hand, by doping zinc oxide with elements such as aluminum and gallium, which are also N-type carrier concentration, have N-type carrier concentration, the electrical conductivity can be increased. On the other hand, an effective strategy to obtain high thermoelectric efficiency is by lowering the lattice thermal conductivity. So the idea here is that by introducing bismuth or antimonium ions, which have a larger ionic radius and higher mass elements into the zinc oxide matrix, this will hinder the phonon-mediated heat conduction, consequently reducing the thermal conductivity. Titanium dioxide is another interesting material. It has interesting optical and electronic properties, good stability, and it has two main crystalline phases, anatase and rutile, which can be mainly controlled by, in our case, by adjusting the deposition temperature and annealing. A cationic doping of titanium dioxide has been documented to improve its electrical conductivity. And again, by adding niobium, we should be able to lower the thermal conductivity. The films were produced by DC magnetron sputtering in high vacuum at the Department of Physics and the University of Minho. Magnetron sputtering has become a preferred method for depositing thin films due to reproducible surface morphology, good adhesion, and long-term stability. We either use a pre-doped composite target in planar configuration in the left, or a confocal configuration with two distinct targets in the right. The films were deposited on glass slides in silicon substrates, mounted onto a rotating support, and heated up to 150 degrees Celsius. We use argon as the working gas to enable plasma formation, and in the case of the system in the left, we use oxygen as the reactive gas. The APT for the APT samples, we deposit directly on the silicon coupon. After deposition, some samples were heat treated in a vacuum furnace for 500 degrees Celsius for 1 hour. So APT was chosen to observe the doping content and distribution of the films, as well as to study the morphology of the grain boundaries. We prepared a total of 5 samples: zinc oxide doped with bismuth, zinc oxide doped with gallium and bismuth, zinc oxide doped with both gallium, aluminum and bismuth, zinc oxide doped with antimonium, and titanium dioxide doped with niobium. APT experiments were done at the KNMF, Laboratory for Microscopy and Spectroscopy at the Karlsruhe Institute of Technology in Germany. The films were deposited onto, again, a specialized coupon directly with prefabricated microtips, which were then prepared by focused ion beam. So this leads to tips of about 200 nanometers thick and an apex radius of 60, diameter of 60 nanometers. The tips were then measured on a LEAP 4000 in UV laser mode. And we used IVAS for reconstruction of the data and used SEM top tip profiles for the shape and shank. Now, starting with the results, we measured the thermal conductivity by frequency domain thermal reflectance at the ICMAB in Barcelona. We saw that the doping of the zinc oxide films with aluminum has a significant effect in lowering the thermal conductivity, being lowered from 6 to 3.2 watt per meter per Kelvin, which we do not see when we introduce bismuth. From the APT reconstruction, zinc, oxygen, and aluminum are homogeneously distributed within the crystals, unlike bismuth, which was not incorporated into the zinc oxide matrix. The bismuth distribution is heterogeneous and it segregates triple points of the grain boundaries, also inducing the formation of thin columns perpendicular to the surface of the sample in the case of the zinc aluminum bismuth case sample. So bismuth contributes to grain boundary scattering of phonons. Measurements were also done for the zinc oxide with bismuth sample, and we do not see evidence of bismuth segregating at grain boundaries. Also, we see a change in microstructure from 3D island growth in the zinc oxide with aluminum and zinc oxide with bismuth to a more regular columnar structure in the case of zinc oxide with both aluminum and bismuth, which limits further reduction in the thermal conductivity. So regarding the sample with both gallium and bismuth, it's possible to carry out the same analysis as the aluminum sample. We do see some spots in bismuth in the top view. However, the bismuth segregation at grain boundaries is not as evident. When we compare SEM images, it's observed that the sample containing aluminum has a more pronounced columnar structure than the one containing gallium. So it will be easier to observe the bismuth lines in the APT. We can use transmission electron microscopy as a complementary technique to the APT. In this case, we were able to identify a higher bismuth concentration in the triple points of the zinc oxide gallium bismuth sample, so reinforcing the conclusion that bismuth indeed segregates. Hence, we can conclude that the proposed hypothesis did not work. The thermal conductivity was not significantly lowered when we add in bismuth. The result can be understood by the fact that, unlike aluminum and gallium, bismuth was not fully integrated into the zinc oxide matrix, so does not substitute zinc in the crystal lattice, but is instead segregated at grain boundaries. On the other hand, when we have both aluminum and bismuth, and gallium and bismuth, of course, this triggers a morphological change where the film's microstructure becomes more columnar, which leads to an increase in thermal conductivity, and thus partially compensates for the effects of the boundary scattering. So in the case of zinc oxide with antimony samples, firstly, the content of antimony is very small. So we were unable to see if antimony was or not homogeneous throughout the sample. we see a clear interface with the substrate, so it's good, meaning the chip only broke after reaching the silicon. And the zinc and oxygen signals are not homogeneous, meaning we can see what is probably a grain boundary, but this is not as clear as the previous samples. So as for the samples of titanium dioxide doped with niobium, at first glance, the results appeared to be quite boring. Everything appeared quite homogeneous. Niobium seemed fully integrated into the titanium dioxide matrix. We did found silicon inside our samples, which indicates a possible contamination during the sputtering process. Over the various tip measurements, the atomic content does not seem to significantly change, even after the annealing process. However, contrary to what it appeared so far, silicon does not appear to be homogeneously distributed. We also see it in tough sims, which implies a continuous contamination indeed. And we see a gradient contrary to the gradient of titanium. So it appears to be an unintentional doping on our parts somehow. So it's substituting the titanium. We do not see grain boundaries, but maybe silicon can help us pinpoint them as it appears to be clustering and segregating a bit at the triple points. So as a bonus, we checked the sample of zinc oxide with both gallium and bismuth after some time after we did the APT measurements, and the sample had mysteriously grown some whiskers, probably due to some sort of contamination. We did try to measure these with the APT, but ended up failing because the whiskers were so brittle and thin. It was just an interesting find to conclude my presentation. I thank you very much for your attention, and I'm waiting questions.
Good. Because we have a little bit like a shift of the time, and do we have any questions here? It is very cool to know that, I mean, sometimes the hypothesis doesn't work. It's always not a very, I mean, you get something at the end. And yes. For this thin film deposition, you know, we also have a pre-sharp silicon coupon. Essentially, you can also directly deposit the film on a pre-sharp coupon, and you directly run the sample. This is definitely that you save the efforts to do the annual annealing.
Yeah, of course. You don't waste so much time in the FIB preparation.
Yeah, exactly. Okay, good. Yeah. So if you have any question, you can put in the chat so we can jump to the next speaker, who is Allah Kukek Sasana. Please introduce yourself a little bit more, because I cannot pronounce the name right. And he's from NPAE. And you can start your talk now.
Yeah, it's Alokik. Yeah. Thank you for introducing. Hello, everybody. I'm Alokik Saxena, and I will be presenting the topic machine learning framework to discover patterns in atom probe tomography data. Now, as we all know, that atom probe tomography provides 3D distribution of the atoms at sub-nanometer resolution with their chemical identities as shown here. The datasets that we acquire from atom probe can contain from 10 to 1,000 million atoms. Once we have collected the 3D positions of the atoms, a number of post-processing steps are generally applied to the datasets to find out the various microstructural features inside these datasets. For example, iso concentration surface construction can be done, or spatial clustering can also be done. Generally, when spatial clustering algorithms are directly applied on the spatial coordinates of the atoms, these algorithms are slow because of the sheer number of the atoms in these datasets. With isosurfaces, however, the challenges are different. Here I'm showing you isosurfaces corresponding to zirconium and copper in an iron-doped samarium cobalt alloy. With isosurfaces, the quantitative description of the microstructure is challenging. Further, for detailed composition analysis, generally the experimentalists have to place the region of interest manually. On top of this, if the dataset contains topologically very complex precipitates or microstructural features, then the quantification of geometry and composition becomes very challenging. Therefore, to address these issues, we came up with certain machine learning workflows. To show the working of our methodology, we have chosen an iron-doped samarium cobalt alloy. The composition of the alloy is mentioned here. So under a backscatter electron microscope images, the experimenters saw certain bright regions or domains, and they saw that they had lower coercivity compared to their darker surrounding domains. To understand this phenomena in much more detail, they extracted APT samples from both the dark and the bright regions as shown here. And here the blue and the green isosurfaces are corresponding to the copper-rich and zirconium-rich phase, which form the cell boundaries for the magnetic domains. And the rest is the matrix phase, which forms the magnetic cells. Now, the aim here is to quantify the microstructure both compositionally and geometrically, and try to correlate the quantifications to the differences in the magnetic properties. Now, the first step in our approach is very simple, that is voxelization, where a given APT dataset is divided into cubical voxels, and then we calculate the composition of each voxel as shown here. Now, the space comprising of the compositions of each element in every voxel is called simply a composition space. In our case, the composition space is 5-dimensional because we have 5 elements in our data set. Here, I'm showing you a 2D projection of a 5D composition space with composition of zirconium on x-axis and copper composition on the y-axis. Now, obviously, each point in the composition space basically corresponds to a voxel in the given data set. The idea is if there are distinct chemical zones or domains forming in the APT data, then they should appear or separate out as separate clusters in the composition space as well. So we applied clustering in the composition space using Gaussian mixture models, as shown here, to extract different chemical domains in the APT data sets. Now, as we know the XYZ coordinates of each voxel, and we also know to which phase they belong to or which chemical domain they belong to, we can quickly go into 3 dimensions. And as you can see, we have quickly segmented the given 3D microstructure into the respective phases. Once we have identified the key chemical domains or the phases in this particular case, we can apply dbScan kind of clustering on the spatial coordinates of the voxel centroids to extract each precipitate as a separate entity, so that each precipitate now can be studied for its composition, orientation, geometry, and thickness. Of course, we have applied clustering on voxels that are 300,000 in number instead of APT dataset atoms, which were 500 million in number. So we get a huge computation speed boost. Now, once we have separated out all the precipitates, we wanted to reduce all the geometrically complex precipitates into plate-like morphology. For example, in this particular dataset, the copper-rich precipitates had a turbine-like morphology, and we wanted to find out the plate-like morphological features that are coming out of it. So to do so, we first divide the given precipitate into certain slices, as shown here in the PCA directions, such that each slice can be projected into a 2D image, as shown in image G. Now, we have reduced a 3D problem into a 2D problem where we want to find these junctions and the plate-like features. To do so, we first randomly select, for example, this orange point. Then we select the neighborhood around this orange point shown by the green color. Then we calculate the direction of maximum standard deviation of this green neighborhood shown by the PC1 vector. This procedure is repeated for all the points inside the green neighborhood. For example, for the yellow point in the green neighborhood, the direction of maximum standard deviation will be given by PC neighbor. So the idea is, if the initially chosen orange point lies in the plate-like features, they will then the vector PC neighbor and PC1 should point towards the same direction, or their dot product should be close to 1. This simple idea is used to segment out the points in the 2D images that lie in plate-like features and the junction regions. Now, as we know the XYZ coordinates of all the centroids or the points in 2D images, we can quickly go in 3D, and then we can eliminate the junction region or junction voxels to get individually plate-like features. However, there is a small problem in the local PC approach that we have used here. That is, for local PC approach, we have to set this parameter R before applying the model to a given precipitate. Now you can imagine if this radius R is bigger than the image itself, then it won't be able to capture the junction. So to circumvent this problem, we first apply the local PC approach to certain precipitates to get around 500 labeled images. Then those 500 labeled images are converted into 5,000 labeled images by using image augmentation techniques. Of course, for each image, then we know its corresponding mask. And we also, in each mask, we know the region which is pertaining to the junction in the images. This image dataset is used to train a unit model, which can do semantic segmentation. Now, if we feed an input image to the trained unit model, it will predict the junction mask as shown here. And we have eliminated completely the need for setting this parameter R for a new precipitate, because this task of image segmentation can automatically be done by the unit. Of course, the initial local PC approach helps to create the initial training data set. Now, once we have reduced all the precipitates into plate-like precipitates, we can now fit triangular grids onto them, as shown here, which takes the shape of the precipitate. And then we can find at each node the perpendicular region of interest, shown by the cylindrical region here. Then along the cylindrical region of interest, we can then find the 1D composition profiles of various chemical species that are present in the data set. This information is also used to find the local thickness at each node on every precipitate. Further, at each node, we can also find the average composition, which is used to basically find out the in-plane composition fluctuations in every precipitate for both the zirconium-rich and copper-rich phases. Further, we were also interested into knowing how composition fluctuates perpendicular to a given precipitate. For example, at a given node, at normal 1, the 1D composition profile of copper has 3 peaks. However, for certain other precipitate, at normal 2, it has just 1 peak. Now, 3 peaks in 1D composition profile of copper means that there are 3 layers of copper perpendicular to the normal in the given precipitate. However, just 1 peak in the 1D composition profile means that copper is more or less homogeneously distributed. Now, we calculate this information for every node in each precipitate that you see here, and try to map this information onto the precipitates like this. Now, here you can see that the dark red color basically shows that certain precipitates have higher tendency to have triple peaks in their 1D composition profile, as shown here, and some of them have just double peaks in 1D composition profile of copper. Now, coming back to the problem with which we started, we were given a bright region dataset and a dark region dataset. Now, the most important difference compositionally that we found between these two datasets is that for the zirconium-rich phase in the bright region, not many precipitates had double or triple peaks in the 1D composition profile of copper. However, that was not the case for the dark region phase, dark region samples, because here double and triple peaks in zirconium phase were very common. Now, we can also quantify the area fraction in these precipitates, how much is basically triple peaks. Now, since we also store principal components for each planar precipitate, we can also find out the relative orientation between the precipitates. For example, how many precipitates are parallel to each other, or what is the angle between those precipitates. So, for example, in this particular case, first we separate out all the copper-rich precipitates by the above methodology, and then we can find out precipitates that are parallel to each other. And we can also find the distances between the precipitates. And this is really important because we are dealing with magnetic materials where these distances are important and can be related to properties. In conclusions, I want to say that the composition space approach that we have developed here is a general methodology that can be applied to other APT data sets of other materials as well. The workflows that we have developed on top of local PC approach that have been built on clustering and composition space approach can extract microstructural features from APT datasets in an automatic and reproducible way. And the framework that we have developed here, of course, open pathways for large-scale statistical comparison of different materials using APT data. And finally, I want to advertise Dr. Markus Kubach's talk tomorrow. He has developed many more interesting tools for dealing with APT data. And with him and some of the colleagues from NFDI and MatWork, we are trying to provide all these tools as Conda packages so that they can be more accessible. With that, I want to thank you for your attention.
Yeah, thank you for providing us with the new method to analyze the data. Do we have any question from the audience? So I think we still have 1 minute, and you showed us the data that they all have a very like older kind of ways. Is this the mid of the pixel? I mean, the voxel, or this is you remove part of the data? I mean, what exactly means this little dots here? I assume this is not our data, or
yeah, these are voxel centroids basically. So
and this is center of the voxel, because then we suppose that okay.
Yeah, this is the center of the voxel. Yeah.
Okay, so essentially the resolution of this method depends on the size of the voxel you choose.
However, all the composition analysis that we do is so the geometric information, yes, it is taken out at voxel resolution, just the geometric information. However, all the composition analysis that is being done, 1D composition profiles are calculated by considering atoms that are present, or the real APT data that is present. So this really gives us a huge speed boost, because you can imagine there are like 500 million ions in the data set. So dealing with voxels helps to work out with the topology.
Yeah, okay, thank you. Just one more thing is, did you upload the code on the GitHub, or this is a shared thing, or this is another way to that direction after publication?
I mean, as I said, it is uploaded on the GitHub, and the links will be provided tomorrow by Markus.
Oh, sounds good. Yeah. Okay. Yeah, if we have questions, you can just put in the chat box. So we move to the next talk with Michael Oysterholz, and he's from KIT, which is a university from Germany. And you can start sharing your screen and start your talk. We cannot hear you. I think your microphone was not connected. And one option is you have a Zoom. You can select the audio and change different microphones. I mean, if you have the Zoom software, I mean, in the background, there is a setting button, and you choose select the audio system. If you don't, maybe try to pull up your current microphone and use the computer microphone.
Can you hear me?
Yes.
Okay, so I don't know why this didn't work. I checked it before.
I think I can hear you clearly. You can start. Yeah.
Okay. But the slides are, you can see the slides, right?
Absolutely. Yeah, you can put on the presenter mode and start your talk.
Okay,
Good.
great, thanks.
Yeah, all good.
Okay, so thank you, sorry about that. Hello, everybody. So the subject of my talk are interfaces in refractory metal and refractory ceramic composites. And I will present you some of my work where I employ scanning electron microscopy methods for microstructural investigations and APT&M for more nanoscale phenomena. So the motivation for this material class of refractory composites comes in our case from high temperature processes such as metal casting, where parts like lining parts are conventionally made from aluminum oxide ceramics. And one part I would like to highlight here is the so-called spider brick. As you see here on the slide, on the right-hand side, it's a part that accepts the melt that is poured into this cavity here and distributes it into the different directions here on the side through the cavities here. And you can imagine this part is first at room temperature and is then, so it then gets into contact with a 1500 centigrade or so hot melt and is therefore highly prone to failure by thermal shock. So the idea now is to add metals and also to adjust mechanical properties of these materials, but especially to enable the electrical conductivity. So to make resistive preheating possible, and by this bringing down the thermal gradients and prolong the service life of such parts. So we are looking for melting temperatures of the metals beyond 2000 centigrade, and niobium and tantalum are good candidates because of the similar linear thermal expansion coefficient when compared to alumina. So yeah, in our case, these composite materials, they are prepared by different means. So we have also called isostatic pressing or additive manufacturing. So 3D printed parts may be possible here. But what I'm showing now here, this is a sample that has been sintered conventionally. So pressureless sintering held at 1600 centigrade in argon. And beside the obvious raw materials, the powders, we have also different sintering additives, so binders and water additions. And the overall aim of the project here is to investigate what could be effects of contaminants, and do we have any reactions of the main phases with each other or with the environment. And here on the right-hand side, this is from a study we published earlier this year. This is a phase-segmented backscatter electron overlay image, and indicated here in yellow. So we found that there is niobium oxide forming in the microstructure. When we look at this isothermal section at 1600 centigrade, so the sintering temperature of the aluminum niobium oxygen system, we can figure out why this happens. So with the aluminum oxide and the niobium solid solution up here, we are working here on this red tie line if there is additional oxygen in the system. So for example, in the sintering atmosphere, then niobium can take up to 6 atomic % of oxygen at this temperature. However, if the temperature then drops to room temperature, this value changes to less than 1%. So if we decrease the temperature, so we cool down in the furnace, we will end up in the yellow phase region forming niobium oxide. So this was a more broader view on what would happen in the microstructure, but we're especially interested in what does additional oxygen do to the ceramic metal interface. So because this will affect the cohesion of metal and ceramic, and therefore the overall mechanical properties. For this, we sputtered niobium with magnetron sputtering on alumina substrates, so sapphire substrates with a defined orientation. We did this at room temperature. Yeah, you can see here the samples, and the idea is to to selectively investigate the exposure to oxygen by comparing the states of as deposited and with after an annealing treatment that we chose to be at 1600 centigrade to mimic what would happen to a sintered sample. So this is the as deposited state. We have a TM micrograph here with the sapphire substrate here on the left and the niobium on the right. There are three main takeaway messages here. So first of all, apparently the niobium grains here, they grow with a fiber texture on the alumina substrate with the 110 planes parallel to the basal planes of the sapphire. Also indicated here in red, these are grain boundaries. So this fiber texture has fiber widths of up to 20 nanometers. So by this, we have a high grain boundary density. And then lastly, there is no apparent reaction at the interface, so between ceramic and metal at this temperature. If we compare this with the 1600 centigrade treatment, we see that there is now essentially two different regions. So we have the apparently untouched interface, but we also form particles. One of them is shown now here in this micrograph. If we do EDX profiles in regions without and with particle, we see that without the interface appears to be compositionally sharp. So meaning there is the gradients are sharp here, and the niobium solid solution appears to contain a certain amount of oxygen. And in the case of the particle below, we see that the composition at this position here is different from the two sides, left and right. And these particles have widths of up to about 20 nanometers. And apparently, this is another observation here, they appear at interface irregularities. So this bend essentially here at the interface, that could be a preferential nucleation site. And at niobium grain boundaries, as is indicated here by these two different SADs of the adjacent grains. So now we targeted these two different regions with APT. So this is now what a tip from a location away from such a niobium grain boundary. So if we draw a proxygram for an isosurface of niobium with 38 atomic percent here along the interface, we essentially just see there, if at all, then it's just an interdiffusion zone. We have somewhat increased oxygen amount in niobium, but we couldn't find any hints for clustering here on the niobium side. Now comparing this to what, so when we targeted a location at such a grain boundary, the big difference that we can see already is that there is an intermediate region in the tip that is rich in niobium and oxygen containing species. And if we now look at an oxygen concentration map of this tip, we see that here now we targeted such a triple junction of a oxygen decorated niobium grain boundary with the ceramic metal interface. So apparently there's oxygen supply through the grain boundary to the interface. And if we then check the aluminum concentration map and take a slice of the interface here indicated with the black box, we can distinguish two different regions on top of each other. So one, the aluminum rich region, which we could assign as aluminum oxide, and then a lean region that is probably a niobium oxide. So if we then draw again a proxygram, so here where the red arrow is, so through this aluminum lean region, we can see that this composition here in between rather hints at niobium dioxide than niobium oxide. We again have a considerable increase of oxygen in the niobium solid solution, but again, we couldn't find any clustering. But at this high level of oxygen in niobium, this gives us the impression that we are only at the early stages of niobium oxide nucleation and growth here. So overall, oxygen diffusion along such grain boundaries to the interface appears to be responsible for a nucleation of such a interfacial oxide. And then lastly, what would happen for an oxygen overexposure treatment? So we have here now a lower temperature, but much longer time. And in the tip here, we have alumina on the left and the previously niobium on the right. And we see here that after this treatment, the niobium side on the right has a niobium oxygen ratio that corresponds to the niobium pentoxide. So we moved all the way down on this blue arrow to the pentoxide. However, we also see that there is about 5% of aluminum on this side of the tip. And since there is no solubility for aluminum in the pentoxide, this means we had a reaction of this oxide with the sapphire substrate, and we formed ternary oxides. So to conclude, we have on the one hand side, we have if there is fast oxygen transport through the grain boundaries, we have the formation of such particles at the ceramic metal interface, while the bulk itself, so the niobium bulk, remains metallic. Apparently, such irregularities at the interface act as preferential sites for nucleation. And if there is no supply, the interface appears compositionally sharp. And then for more severe oxidation of the interface region, we will form niobium pentoxide that can then react with the alumina to form ternary oxides. So with this, I would like to thank the German Research Foundation for funding and you for your attention.
Thank you for the talk, very interesting results. Do we have any questions? Yeah, and you can go ahead, Cerium.
Yeah, thanks. I just wanted to ask a question. Often we see in niobium that's like a hydrogen sponge, and also in atom probe we see a lot of hydrogen when we measure niobium. Do you see that as well, or?
Yeah, absolutely. So we usually have the satellite peak after the main niobium peak.
Yeah.
What we did so far is we just said for now we will disregard this and
Okay.
count it as niobium. Yeah.
Okay, thank you.
Yeah, and I'm wondering, like, for this non-oxygen supply, and you say you have a sharp surface, a sharp interface. I'm wondering, did you see any detection of a thin layer of niobium oxygen at the interface region?
Yeah. So wait a second. So you mean here, essentially?
Exactly. Like, did you by the mass spectrum, did you see an atomic layer of niobium? Oh, so you pointed out here. Okay.
Yeah. So normally no. So so niobium itself, if there is no additional oxygen in play from outside, then it would not react with the aluminum oxides. So only the niobium oxides would then react with the substrate.
Yeah, okay, good. And it's interesting to know that if you can check if the interface there is some detection of niobium oxygen species, because this is what Emmanuel Marquis and also during my PhD, they see the thin layer where it goes from oxides to metal. There is always a bit of, you can say, artifacts or just a co-evaporation effect, and this is worth to check. I mean, I'm just curious if you see similar thing. Yeah. Okay, thank you for your talk. And we jump into the next one, which is Nikita Paulin, and he's from MPAE. And you can start sharing screen, and yeah, and your microphone is currently muted. And you are still muted. I can ask you to unmute.
Yes, it should work
okay.
Now, right?
Good. Yeah, okay, yeah, you can start now.
Yes, thank you very much. Yes, hello everybody to all around the world. My name is Nikita Polin. I'm a PhD student at MPIE, and today I'm going to tell you what we could learn about cerium cobalt magnets from atom-probe tomography. So another material system, happy to contribute to many other interesting material systems we've learned of materials, batteries, and minerals. So here is the magnets coming. So today I'm going to tell you why you should care about magnets, why APT them, and why exactly cerium cobalt copper. I will jump into the results and conclude at the end. So why should we care about magnets? Basically, it's a matter of energy conversion. If you think of electrical devices which convert energy from current to movement or vice versa, it's always or almost always a hard magnet involved in there. So if we improve those hard magnets inside, we can improve energy conversion. So save more energy or gain more energy, which is beneficial. So how does a microstructure of such a magnet look like? Where you characterize a magnet by a BH loop, external field and internal field. And the microstructure looks is following. We have matrix phases, which are cells around 100 nanometers size, and cell boundaries, which separate the cells about 10 nanometers thickness. And above that is a domain structure. So it means in each cell, a magnetic field can show in a certain direction, left or right, let's say here. And in the beginning, at zero, the external field and magnet, which is not magnetized, they are more or less equally oriented to left and to right, so no magnetization. If we then magnetize a magnet, what happens is that all the magnetic domains show in the same direction. When we turn on the field for hard magnets, it remains the same, and we are left with the remanence field. If we then demagnetize a magnet again, so in the reverse direction, what happens is, again, some of these domains flip again. And this field where this happens is called coercivity. And this is happening because some of the information of one domain is transferred to the next domain. And it's actually the cell boundary phase which is hindering this. So which is a resistance for passing the information from one domain to another. So if you have a good cell boundary, then this won't happen so much, and the coercivity will be higher. If the cell boundary phase is not well working, then the coercivity value is low, and then the information is passed over very quickly. And this is not what we want. What we want is to have both values as high as possible, remanence and coercivity. But as I mentioned already, we have a problem. There is a Brown paradox, and the practical performance limit of such magnets only 30% of the possible one, and it's basically due to this microstructure-related issue with microstructure and composition of a magnet, because the cell boundary phases are not as good as they could be, and they reduce the coercivity. So what we want to do is we want to look at magnets, how they are microstructurally engineered by APT, and then make sure that we use the insights to create a good magnet and enhance the energy conversion. So why should we study cerium cobalt magnet? Well, the answer is because it's very similar to the samarium cobalt magnets, and this is actually a commercial magnet with a small market share, but it's actually better than the one magnet you know, the niobium iron boron, for high temperature applications and aggressive environments. So here the energy product is of niobium iron boron is quite high, but samarium cobalt is still very good, and as I said, in some applications it's better. And from scientific point of view, samarium cobalt is less explored than niobium iron boron, so there's a lot of things to learn. And for example, what we can learn is the cerium cobalt copper system. So it's a hexagonal system. It is cheap. So the cerium is located here, is the same group as samarium. And this phase with cerium 1 and cobalt copper 5, we also have in the commercial samarium cobalt magnets. So they are relevant and we can learn something. We have a decent magnetic property still, so it's been known that we have a coercivity around 1 Tesla. The very good magnets get 3 Tesla, but still 1 Tesla is quite good. And especially when we add some copper there. But the thing is, the microstructure of these magnets was not investigated since the 70s. The people have looked much more into the commercial magnets, which were already quite well developed, but they did not look in detail in the very simple and maybe not so good magnets, which are the bases. So to our understanding, the microstructure is unknown, and the best images that we have look like this. So that's why we went for atom probe, or TM, SEM, to look at these magnets in more detail. So we'll jump into the results now. The magnets that we investigated were produced by induction melting from pure cerium, cobalt, and copper elements. Then we aged them in argon atmosphere and water quench with a composition of, which is noted here, with a little bit of copper. So the first sample, high coercivity sample, we call it, was annealed at 1000 degrees and quenched, and then again at 400. And here it is in the region where we expect a decomposition, because we are in the miscibility gap. The second sample was produced the same, but additionally it was annealed at 1000 degrees in the homogeneity region, so we expect something more homogeneous. From the MH loops, we see that we have different coercivity. Here we have high coercivity, but here we have low coercivity. So the open question is, what is the micro and nanostructure of these magnets? To answer this, we employed SEM, BSD, TM, and APT. And in the end, if we're lucky, can we link the nanostructure to the coercivity, so establish a structure-property relationship? So this is the results from the structural analysis. From BSE, the image that you see here, we see that we have large grains, size around 100 to 500 nanometers. And from EBSD, you see it's more or less the same color. We have very small misorientations, and this is what you want to have for a magnet. It should be completely textured. All the C-axes should point in one direction, and we have it here. From HADA-APT&M imaging, from the high-resolution imaging, we see the expected 1,5 structure with cerium in the middle and cobalt around. And from the low magnification images, we see contrast variations. So here there are some bright regions and some darker regions. And it's probably because we have some copper-rich regions, and we expect something like this also from the phase diagram. And we know that the atomic number is a little different for cobalt and copper, so that's why we expect some kind of contrast. But still, the question remains open. How are these copper-rich regions arranged? How do they look like? Which shape do they have? So this we cannot answer from TEM, because here we have a 2D projection, and again, the difference between those two atoms in atomic number is low. So APT is the way to go. Let's look into APT results. So here are the maps of high versus low coercivity. If I take a 2D counter profile of copper here, we can already make some observations. We have elongated copper poor and copper rich regions in both samples. They have a round alveolar shape, but in high coercivity, we have a high chemical separation. In a low coercivity, we have a low chemical separation, so a more homogeneous sample. See this because we have a more homogeneous color, while here we have some orange and deep blue, which we don't find here. We can also look at 1D profiles. From here, we can see that cerium concentration is constant in both samples, as we expect that the exchange is only on the cobalt and copper subledges. So that if copper is high, then cobalt is low. And what I can do is just count the frequency of the concentration of copper occurring. And what I can see for high coercivity sample, that I have a lot of low concentrations of copper and very high. But here I mainly have a lot of concentration in the middle. So again, the frequency distribution analysis confirms the higher homogeneity and now quantitatively. And if you look more closely into the high coercivity sample, what you see here is we have a preferential orientation of alveoloids. But I could not relate in this measurement where the C-axis of my sample shows. So is it showing like this? Maybe it's showing perpendicular. Is it some special crystallographic direction? So this I didn't know, so I decided to do a second lift out. And for BSD, I already knew that the C-axis of my crystal is oriented at 43 degrees to the sample normal, as you can see here from the pole figure. So in this blue region, I know that I need to tilt to 43 degrees to have my C-axis pointing up. And this is actually what I want to have. I want to have an APT needle where I know the C-axis is pointing up. So together with the technician at the API, we decided to do a special lift out at 43 degrees. So this is a lift out, you know, at 0 degree, you cut, and then you lift out on silicon compound, and this is how it looks. But what we decided is at the last point before we take out the lamella, we tilt the stage to 43 degrees and then do the lift out. And in the end, this is what the lift out looks like. We have a tilted lamella at 43 degrees. And here I expect the C-axis to point up. I did the sharpening. I needed to add some platinum by SEM because the platinum deposition was not very good at 43 degrees. This worked, and then this is how the tip looked like. So now I need to check if I was successful with C-axis pointing up. And actually, I was. Sorry? Okay.
No worries.
Yes, so in the detector histogram, I found a pole in my measurement. So the 0001 pole was appearing in the detector histogram. And if I look also, I could find the atomic layers of 001 almost parallel to the z-axis. So I was lucky with that. And I calibrated the cobalt distance to the distance of 0.4 as it is in the crystal, because I have some cobalt-rich layers here. So now I'm looking at the precipitates and how they are related to the C-axis. Here already you can see some copper-rich regions. And if I draw the isosurface at 4 atomic percent copper, so I look at the copper poor regions here, I see that actually they are elongated. They are some like channels or long cylinders, and their long axis P has a preferential direction to the C-axis of our crystal. So we have only small angles deviations from the crystal orientations. And another interesting point, if I look at the pole and I see such a copper poor channel here, I do not see any difference in the atomic planes. So the precipitates are coherent. We get the crystallography also from the atom. Yes, and you see the precipitate directions are almost parallel to the C-axis or only smaller. And I could also see it in the 2D counterplot. So here is a copper concentrations, cobalt concentrations along Z, X and Z. And here I again see some slight preferential orientation to the C-axis of my precipitates with size around 5 times 10⁻⁵ to 20. I see a cell structure along Z also here. So we have a copper poor channels embedded in copper-rich walls, which is actually compatible to the 217 commercial magnets. Here we also have cells which are copper-rich. So this oriented cell structure is a good pinning center as for the commercial magnet. So we have answered the question, how does the microstructure look like and why does it cause high coercivity? With this, I can conclude. We found 2 samples with high and low coercivity, but on microstructures, so we did some analysis, and we could find from high coercivity, we have high concentration gradients, strong chemical separation. Along the C direction, we have copper poor elongated channels oriented at low angles, and they have a high strength of pinning centers, and this deduces the high coercivity. Low coercivity sample was done with the additional annealing step in homogeneity region and the phase diagram. And it makes the elemental distribution homogeneous, which we also see. Also, the preferential order of the precipitate seems to be lost. So we have less effective pinning, which reduces coercivity. So for the first time, we reveal the nanostructure of these magnets and find similarities to cell structure in the commercial 217 magnets. It was impossible before by TEM because the precipitates are so small and cobalt and copper are so similar in atomic numbers. It was not possible without atom probe, and we did this now. So the next steps are Lorentz TM to see domain wall structure, Lorentz TM with external magnetic field to see how it reacts, and micromagnetic simulation of the coercivity mechanism. With this, I want to thank you for your attention and also thank to all my collaborators and the funding.
Yes, thank you for the very, very nice talk. Really interesting result and showing what APT can do when the TEM have difficulties. So because of the time limit, I think, Fred, if you have a question, do you think you can post in the chat box and we will move on? I think it's nice to see this discussion actually for everyone. And we jump to the next speaker because we are 4 minutes late from the schedule. So our next speaker is Kasper Honestand. I hope I pronunciation is right. And he's from Norwegian University of Science Technology. And you can start sharing the screen and start your talk.
All right, thank you. Can you hear me?
Oh, good.
Okay.
And you can put in the presenter mode of your presentation. Yeah, good.
Yeah,
yeah, you can start.
Good now?
Yeah.
All right, thank you. All right, so thank you for the introduction. So today I'll talk about how we can use the atom probe to image and also do chemical analysis of multiferroic thin films and superlattices. So hopefully it will be clear during the talk how we can go from this kind of chemical maps to really say something about nanoscale ferroic phenomena. Right. But first, let's start with the general introduction to ferroic materials and phenomena. The last speaker already introduced magnetic materials, but ferroic materials is a bit bigger topic than just magnetic materials. So the most general way to characterize them is through a long-range order. So in general, you have a unit cell that has a polarization, magnetization. Sometimes it's elasticity or toroidicity. But this is typically ordering on a long-range scale. As you can see here to the left, like you have a single domain with a long ordering that is kind of uniform. And you can go to a second domain where the orientation is changed. So this is perhaps one of the most defining properties of ferroic materials. And what is also necessary is to have kind of a control of this ordering through external stimuli. So for instance, for a ferroelectric material, you would have a polarization as your ordering inside the unit cell. And in that case, the external stimuli would be electric field. So if you apply an electric field, you can switch the ordering from a multi-domain state into a single domain state. And this, of course, is reversible. So you can go from the one single domain state to the opposite direction. And while doing so, you will typically see this hysteresis effect, which historically is also the first sign of ferroic behavior. And it's very defining properties of ferroic materials. So because of how these work, they are quite commonly applied for electronics, making memory devices or capacitors, for instance. But on this talk, I want to go a bit beyond just ferroic materials and talk about multiferroic materials. So in these materials, you have a coupling between several order parameters. So you don't just have a ferroelectric material or a ferromagnetic material, but you have actually coupling between them. So you have a single unit cell with both present, and these are kind of intertwined in a specific way. So one of the most interesting coupling is through the magnetization and the polarization, because this would allow you to control the magnetic domain structures with electrical stimuli, which is very power efficient and is suitable for making memory devices. But getting exactly this kind of coupling that you want is quite tricky. So a very common strategy to try to achieve your specific properties is through interface engineering. So using like MBE, PLD, you can really achieve incredible atom by atom control of your deposition, control the thickness, strain, termination, really design structures to get specific properties. So in the multiferroic community, one really perfect example of this was lutetium ferrite superlattices. So these were first presented by Julia Mundi in 2016. And here they had two materials that they wanted to grow in a superlattice. So one was lutetium ferrite in a 1-2-4 configuration and in a 1-1-3 configuration. And the main difference here is just that the 1-4 is magnetic and the 1-1-3 is ferroelectric. So they had the idea that if you take these two materials that are compositionally and structurally quite similar, but in terms of functional properties, they're very different. If you then grow these together, you can then couple together the properties. So they did exactly that. They grew big blocks of the ferroelectric phase that you see here, and then this kind of disconnected from the other blocks by a single monolayer of the 1-4 phase. And what they then observed is that when you switch the ferroelectric domains with electrical stimuli, you also switch the magnetic domains to really achieve the true room temperature multiferroic material, which was a long-standing goal in the multiferroic community. Now, again, I want to go back to what I said before and really emphasize that this is a perfect example of interface engineering, because all the coupling happens at these two interfaces here. Now, what you can additionally see in this material is that you actually have a quite interesting coupling on a local scale. So for instance, if you look at the ferroelectric domain structure, so this is a high resolution TM photo showing the domains of the ferroelectric phases. So for instance, blue is polarization pointing down and red is polarization pointing up. What they actually observed is that closest magnetic phase, the polarization is very often pointing out of this layer. And this is a very strange configuration to find in a ferroelectric material, because whenever we have a polarization of a domain meeting head to head like this, or tail to tail, then you build up electrical charge. So typically they would be parallel instead of facing each other like this. So this kind of scenario is very strange to have, but this is still how the structure looks like. And of course, what you're missing here to really explain this properly is the defect structure. So specifically in the ferroelectric material, the defects are incredibly important because these are very insulating materials. And if you add the defects, these are, of course, electrically charged and they provide charge carriers. And that's going to completely change how polarization can exist and also how we can control it with electric fields. But using the TM techniques that they had available, then of course this one's not really information that was available. So what we want to do here is kind of extend what is possible in terms of chemical analysis of oxides, specifically ferroelectric materials, and use this to kind of say more about the functional behavior that we see when we explain the properties that we observe. So yeah, atom probe tomography, you're all familiar with that technique, of course. So it's very common to apply for metals because it has really good chemical accuracy and sensitivity, but also combines this with good spatial resolution. So oxide and semiconductor, it has a much shorter history, as you know. But for ferroelectrics, it has almost no history at all. So when I started my PhD, almost no papers could be found on this topic. So what we first wanted to do then is to really take one of our ferroelectric materials that we work on quite a lot and just try to benchmark it, try to kind of find the limit between sensitivity and spatial resolution that you can kind of see on the edge here. So we then took one of our single crystals that we have worked on quite a lot, and it's very similar to the lutetium ferrite that I introduced earlier. So this material we doped it with 0.04 atomic percent of titanium, and the matrix is composed of erbium, manganese, and oxygen in this kind of structure. So this unit cell structure here is actually accurately representing the composition that we have with one dopant of titanium per 3,000–4,000 of the matrix atoms. Now, because these materials are quite insulating, we have to use focused ion beam to make the needles. We can field evaporate samples and see that they behave quite nicely. And already here we can see that titanium can easily be separated with no secondary phases or clustering seen. And if you zoom into the core of needle, into the 001 pole, you can even see atomic really solid planes and really place dopants on specific atomic planes. But this is still all for bulk system, single crystal. So what we want to do now is move on to thin films. So we start by preparing the thin films from using our focused ion beam. So now the main difference is that we have to introduce capping layers at the top simply to protect the thin film from the ion beam. And also because the thin films are quite thin, of course, we have to increase the width of the film by introducing this chromium capping layer. So we start working on the ferroelectric lutetium ferrite. Sorry, so the 113 configuration of the material. We then put it through the atom probe, evaporate it, and then get this chemical maps. And already here we can start to see that it behaves quite nicely. We can even zoom in and also see atomic resolution in the thin film. But what we're most interested in here is the interface effects. So what we now look for is the chemical composition from top to bottom. And this is what you see here on the right. And immediately you can see that the two phases are quite nicely represented. You have the ferroelectric phase here with the expected composition, and the same with the substrates. But if you look at the interface to the substrate and the ferroelectric material, you see that you have a quite nice deviation. You see a drop in oxygen, and you see an increase in iron, and a drop in lutetium. And this kind of change in composition is very accurately corresponding to the magnetic 1-4 phase. And these two phases are quite interlinked and quite common to kind of grow lutetium ferrite thin film. And apparently it's then possible to see this kind of substrate-driven phase change in your material. And it's quite, of course, important for the functional properties, because that means you basically start growing a material with a completely different phase, and that's, of course, kind of influence how the electric field is kind of control the polarization as you grow the thin film. But now we want to move over to the superlattices. So we want to study the interfaces a bit more carefully. So what I showed before was the quite abrupt change in structure from the substrate to the thin film. But now we want to look at the much more subtle interfaces between two very similar materials. So we start by imaging it with high resolution TM to just see the structure is preserved, and we see the kind of layering and change in the domain structure. And then we put it through that and probe to get the chemical maps. So already here you can start to see some differences. You see that you have these dark lines here. So this is because we only use iron here to visualize the thin film. And looking at the composition of the unit cell, you see that iron is the main change that happens. Iron is enriched in the magnetic layers. So these dark lines and directly corresponds to a single monolayer of this magnetic phase. Now, we then go ahead here as well to make the chemical profile from top to bottom. And here again, you can immediately see that looking at iron, you see, for instance, large peaks at the dark lines, and a corresponding drop in lutetium, exactly what you would expect from the TM images and the unit cell. But now, of course, we can also see the oxygen profile with this new atom probe data. And that is quite interesting because now we can really be quantitative. So what we do is that we focus on just a single of these monolayers, as we see here, and create a model based on DFT. So this model is based on a perfectly ideal structure with no defects introduced at all. And basically what we see is that the iron and lutetium is quite nicely corresponding to this idealized structure. But in addition to that, we see that oxygen is not corresponding. Sorry, my throat is just not working today. But what we see is that the oxygen is deviating quite a lot. And this depletion of oxygen is then directly corresponding to oxygen vacancies in the material. And here we can even be quantitative and really get a number for the density of oxygen vacancies that you can find down here. And why this is so interesting is because, again, these materials are really insulating. So if you introduce this kind of structural picture that I see here, it's kind of strange to see the unknown because you build up electric charge that cannot be easily screened in a typical insulating material. But if you include the oxygen vacancies, this picture really becomes much more understandable because oxygen vacancies can be acting as charged positive carriers at these layers, really screening the bound charge from the polarization. Which is something you can only know after you have this kind of chemical information. Then secondly, it's quite well known in this material that the magnetic properties are directly linked to the oxygen stoichiometry. Not just the strength of the magnetization, but also the onset of the magnetic phase is directly related to the amount of oxygen in your material. So in other words, the kind of defect changes that we see is going to directly kind of influence exact functional properties in the material. But we still have some further work to really decouple how much of the functional properties is really stemming from defects versus how much is really stemming from the structure of the materials. So with that, I would like to conclude my talk on applying atom probe tomography to multiphotic thin films and superlattices. So in summary, we managed to obtain chemical maps of multiphotic thin films and really get new insight into defect distribution. And we'll use this to explain quite unusual ferroic phenomena in a set of multiphotic superlattices. So thank you for listening, and if you want to check out more of our atom probe results, you can see our papers there. Right, thank you.
Yeah, thank you for the talk. And do we have any questions? Thanks for showing this state-of-art HRTM images. You see this phase field up and down, and I'm wondering, I mean, if you have such an effect in the HRTM, what do you expect that APT can tell you in terms of compositional changes?
You mean this image here?
Yes, like if you do kind of like a correlative TM, APT, like what do you expect if there is a certain compositional change in this phase field and up and down regions?
Yeah, I mean, that's kind of what we wanted to look at here, what happens when you see this kind of change in the boundaries. If you have a compositional change here that you can only see from the atom probe data. But so far, the only change we see is occurring in this magnetic phase here. So in this single modulators, that's only where we see the oxygen vacancies. At the boundaries themselves, they seem to be quite defect-free.
Yeah. Okay. Yeah. Okay. Thank you, everyone. I think thanks for the speaker, all the invited speaker, and all the speakers. I think we'll have a very interesting talk to see all the applications in all sort of materials. Now is the time for a coffee break. And we will come back in, I think, 35. Yeah, 35 for the next session. And I hope you enjoy your coffee and yeah, see you soon.
Nanjing, the capital of Jiangsu province, is an ancient capital of the Six Dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan Scenic area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of one university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 Project, a member of 985 Innovation Platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities, and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert
Hello, everyone. Good afternoon, good morning, or good night. Welcome back to the session. The topic of this session is about open software workshop and specimen preparation. This is Yuan Wu coming from University of Science and Technology, Beijing, China. In this session, we have 4 speakers. One invited talk and 3 oral presentation. The first speaker is Dr. Daniel Halley from Oxford Atomic Limited. He will talk about software advances to make APT fundable, accessible, interoperable, and reusable. Before Dr. Halley's talk, I would like to give a brief introduction of Dr. Halley. Dr. Halley is the co-director of Oxford Atomic Limited and visiting research at Oxford University's Department of Materials. His work has covered the development of new data analysis methods and the software characterization of materials, experimental protocols, and add-on systems for instrumentation. His work on experimental methods include novel 3D mapping of deuterium via a combination of electrolytic and cryogenic APT, as well as the development of new hardware to enable complex experiments. In data processing and software, he has researched new reconstruction algorithms to enable distortion-free imaging in APT experiments, working across diverse materials from alloys to semiconductors. He is the lead author of open source APT software such as 3Depict, which provides interaction visualization and analysis of large-scale APT data. Dr. Halley will be presenting examples from his research, which highlights how modern data sharing in conjunction with new open source algorithm can be used to promote and advance APT data reconstruction and imaging. This work has been conducted at the University of Oxford, starting with simple models for level set methods, as well as more complex and complete multiple physics simulation to show how moving front methods can be applied to solve advanced APT reconstruction problems in a matter of hours. Dr. Halley, are you ready to go?
Yeah, thank you very much. Start sharing my screen here. Yes. Sure. Okay. Can everyone see this?
Yeah.
Great. Okay, so thank you very much for inviting me here today, and thank you everyone for attending. So as discussed, I'm talking about software advances to make atom probe findable, accessible, interoperable, and reusable. And so I think, one of the things that I'm going to be talking about today is, a little bit about the environment in which we work and how we do things. And so some of the work that you see today is work coming out of the University of Oxford. Some of this work from my time at MPIE and a couple other places as well. And so at the moment, I'm co-director of Oxford Atomic, as discussed, and that's the banner we're working on today. So what is fair research? And so fair research is a sort of idea that's been around for a while, and it's started to coalesce, and it's appearing up more and more in everything we do. And it's the idea that we should be encouraged to make sure that our research is being extended to as wide an audience as possible. This has to be in a way that is findable, and so without requirements such as author contact. And so there was a paper in 2016. It's linked down the bottom, and it's talking about the idea that software data and all your research needs to fit under several categories and check several boxes. And so it's this idea called FAIR. And this is being increasingly directed by grant agencies across the world and is being supported by digital archive services such as the Oxfile service we have at the University of Oxford. And the idea is that, we want to be able to check these four concepts within here. So, I'll touch on each of these concepts as we go along, but it's the idea, I'm just going to go again, findable, accessible, interoperable, and reusable. And so, what are the things that are being covered by these things? So in FAIR, we will, obviously cover our papers. This is sort of the things you start seeing about open access. And that means, you can access your papers from the various repositories online without having to go through any kind of author sign-in. When we work in industry, that's very, very helpful because it means you have access to a much larger audience. People working in industry no longer say, okay, I don't have an institutional login for this thing. They can come and look at your research and start to contact you directly. So the other thing that's been coming out of this is data availability. So what we need is, to make sure that not only do we have the paper, but we also have the information that went into making the paper. And so, if I'm looking at an oxygen profiles, I can go and search for this online. I type in oxygen profiles into my database, and here I get some data about oxygen profiles across time periods, thousands of years, and that information is there and it's available and it can be found. And so it's about making sure that this is present for your researchers and making sure that that's available. So this includes not only your data, but also the things that go into making your paper. So this could be source code that's used for software to analyze the data. This could be spreadsheets that you've put together, cover all the metadata for your presentation, for your research. And this, as I said, is something that's being required by funding agencies. So let's just have a quick look across, some of the things that we see, some of the statements we see when we have grants. So if you're applying for a grant under Horizon Europe, that's running from last year through 27, you'll see that open access to the data deposited has to be as soon as possible. Okay, that's a statement, it's a condition of the grant. And it must be in line with the FAIR principle. So here we see the whole FAIR thing coming up again. And interestingly, they include the idea that it must be machine actionable. So that means that not only do you need to be able to make your data available, it needs to be there in a way that a computer can automatically interact with that without having a human in the loop there. So the UK here, the UKRI, so they say something that's a little bit different. They say that they go have a sort of precondition step, and they say you must demonstrate that no suitable data is available for reuse. So that means you shouldn't be doing an experiment that's already been done and the data has been made publicly available. That's a condition of getting the grant. So you have to be able to show that there's no data available and that you're not going to be able to just repeat something that's already existing there. And also, again, making that research data available in a timely manner. And they give a fairly clear qualification on that within 3 months of the grant ending. So once your grant is ended, all of the data that has been generated throughout your research must be made available. And we also see this in the USA, federally funded research. I realize it's a bit more of a wider scheme than just federally funded research. But if you have a federal grant, you must be able to provide broad, equitable, and maximally open access to data sets and their metadata free of charge in a timely manner after submission, or whatever timely manner could be interpreted to be. But if you're in your KRI, it's fairly clear, it's 3 months. But I know a lot of people will say, okay, that's all well and good. It's just another piece of work that I have to do to be able to do my research. I'm already very busy. And as researchers, we know we are exceedingly busy. So a key concern, therefore, is like, how does it affect me? Or why is it useful to me to be able to talk about FAIR data and be able to talk about accessible data? Some people don't believe that reuse of data is really a thing, and it's just a sort of wishy-washy, hey, this is something that you could do and everyone is going to talk about it, but actually we're not going to do it that much. But within my research and within work that we've done, actually it's been pretty important. And it's been be able to build up some of the fundamental structures that we need to be able to do our research. So I'm going to outline a few practical examples from our research where this has been beneficial. And so, I do think this is something that is often explored or discussed within the Atom Probe work. And I think that data reuse is unusual. But again, there was 2 prongs to what we were able to do with our work, and I'll touch on these. the idea that you can automate some of your data processing. So that's part of the sort of machine actionable things that I was talking about before. And the idea that you can reanalyze experiments. So not only can we look at experiments that have, we're doing now, we can go back to earlier experiments of our own or experiments of others and start pulling out more knowledge from those experiments than we had before. So often this means synthesis. We're combining different pieces of research together to be able to say, okay, what is the latest view of that research, and what is the amount of information that we can pull out of it. So I think you've probably already seen from one of the at the start of the conference during the Mueller talks, we did work where we automated some of the atom probe analysis. And what we did was we set up a piece of software, a fairly basic piece of software that allowed us to export data completely automatically from our internal repository. So if you have a leak-based system, you have a database, you can have a bunch of files, you can go in there, look at those files and reconstruct that. And normally that would be a very manual process and would take you a very long time to do that. However, we were able to automate that and be able to do hundreds of data sets in one go. And so we were able to do a couple of things out of that. We can identify similar data sets regardless of what's written in the sort of experimental notes or the metadata that's there, because that's not always reliable. And we can start saying, okay, are we seeing some of the phenomena that's occurring within some of our smaller data sets? Is that occurring more broadly across all of the experiments, or is that just narrowly occurring with it? So what we did was we pulled out all the automated data sets, and then we started being able to look at the mass spectra for those. And we were able to look at features within the mass spectra using a sort of basic machine learning approach. Here it's called TSNE. It's a little bit similar to a principal component type analysis, a little bit nonlinear, but the outcome of it is that we actually see that, if we look at these automatically extracted dimensions, we see there's clusters within this. And we can see that, okay, this cluster over here, these are actually predominantly nickel data sets. This cluster in the top is predominantly iron. And the one on the right is silicon, one on the bottom, tungsten and zirconium. And so if we're looking at information from these data sets, we can start saying, okay, what information can we pull out of it? And you can see that we've looked at the H2 to H ratios as a function of voltage within that and looked at the gradient within it. And so you can see that some of these are increasing. So if you look at iron, it's largely increasing except for the sides. Some of these are mostly decreasing, looking at silicon, except for some of the low values. And some of them are a bit more of a mixed bag within those. So zirconium and tungsten ones we were most interested in. And so we were able to show that we saw some actually interesting behavior within the hydrogen. We were able to demonstrate that this occurred across not just one of our experiments, but across the entire database of experiments. This is very reproducible. And we were able to do this very quickly. What that meant was we were able to compare lots of data sets together, and we started seeing common patterns. And so what we saw was that if you looked at non-energy compensated data, we see that the spectra splits into two peaks. It fits into, instead of just having a single peak for hydrogen, we find there's actually two. And we were able to demonstrate if we do deuteration on these experiments, we see that this only occurs here at this initial peak at mass 2. In the deuterated experiments, we would see this split phenomena. And we were able to identify that that is occurring because of the way that hydrogen is interacting with the surface of that tip. And that enabled us to achieve a very high signal to noise ratio within our deuterium experiments to show that, okay, we're now able to say, okay, previously you would have a noise ratio of something like 10 to 1, whereas now we're getting noise ratios of 100 to 1. That means we can localize the deuterium information at a much finer scale than we were previously. And that would not have been possible to do that by hand. There's too much work and too many experiments that would have been needed to do. You would need to do hundreds of experiments. It would have taken an entire PhD. It's just not feasible. But because we have this existing database, we can go and mine it for information. So this is about data mining. Okay. So I'm going to switch tack slightly and say, okay, let's look at historical data sets. So we investigated the hydrogen level variability from historical data. And this work is something that was done at Max Planck Institute. It's a paper that was published by Green et al. And they were looking at a zirconium data set. And they were looking at the interfaces that occur and looking for segregation. And they were showing tin segregation. Now, I was initially very suspicious of some of this data because one of the things that they said was that the H2 peak could be treated entirely with deuterium within the paper. And my student was fine with this, and I was like, well, I don't really know about this. This is unclear. I would like to see a reanalysis of this to make sure that we really are seeing deuterium. And so what we were able to do is go back to that map we saw earlier, pull out all of our zirconium data sets and interact with those and look at the H2 to H variability. And so this line at the top, the deuterium, this with little tiny error bars, was the original line that we gave. And we were able to correct out under the assumption that the H2 to H ratios are fairly constant across the zirconium data sets, which they seem to be fairly reproducible. 0.41 plus or minus 0.15 is for single sigma, 0.3 for 2 sigma. And we were able to essentially correct for that. So that's essentially a kind of down multiplication for it. And you can see actually there's not a huge amount of change within this, much less than I was expecting. I was expecting it to be significantly larger change. And so we see that, okay, although the profile is a little optimistic or a little bit high for the deuterium content that was in the original paper, we can correct for this down to a little bit, and we can say, okay, the ratios are more like 2 to 1 on deuterium to zirconium instead of sort of 3 to 1. And so the zirconium boosts up, deuterium boosts down, tin doesn't do very much. And more or less, actually, this information is pretty good. And so my student was right and I was wrong. And we were able to show that the mean path for this is actually fairly good, if a little bit overestimating what we were seeing. And again, this wouldn't have been possible if we hadn't had access to the original data. We went through and looked at, whether we were able to reproduce this profile within the data set. We were looking at lots of different, angles of that data set and saying, okay, is this something that's a sort of one-off, or is this actually representative of the data? And we were able to show that actually it was fairly representative, very reproducible, and we can actually extend and build up on the work that we did. Looking at our work with the straight bypass data set, you could potentially be more accurate still, but it's not bad, and it is giving you measurements that do make sense and are reliable. And I should be less suspicious of things. So the next case that I'm going to talk about is slightly different. So this was an advanced reconstruction project that was done in conjunction with Kamika, and we built an advanced multiphysics reconstruction suite. So what that means is instead of your typical spherical cap on cone type reconstruction, we were able to look at how the tip shape changes as a function of time. And so we were able to say, okay, if your tip is evaporating, as you go through varying layers, it will take a different shape. It will flatten and it will sharpen as you go through these different layers. That changes your field of view, and that causes that instead of having this straight shank, you actually have a varying shank within here. And you can see that in the bar reconstruction on the left, the sort of sphere on cone model, you don't actually get very good alignment. It kind of tilts up and doesn't really make quite a lot of sense. You see some bends in the layers, things get compressed, and the density distortions are quite wide. If we do a sort of multi-physics reconstruction, we actually get quite reproducible flat layers as we go from side to side, because we've essentially done a little 3D model, run the electrostatic calculations, and looked at how the ion trajectories are going to change as a function of the experimental time. And then we correct for that when we do our reconstruction. So this is what we call the model-driven reconstruction. And this would not have been possible to build without the open source software that was available to us. So it was built on lots of packages, including SciPy, which provides linear solvers and data processing. Packages such as Mesh.io for mesh import and export. It's covering up PTK stuff for quite a while. Seagull library, which is a sort of geometric algorithms library. It has lots of implementations, things ranging from convexal to mesh reconstruction type algorithms, and that was quintessential to what we were doing. Importantly, MedPy, this provided us with the ability to read and interact with some of the hard-def STEM data that was already out there. So our collaborators provided us with hard-def STEM imagery that we were able to build and bring into our model. And without things like MedPy, we wouldn't have been able to do that because we would have had to write the software to do the import rather than just being able to directly import it. And even at the sort of end user stage, looking at the outputs from our software, a lot of that was done through PowerView for our visualization. And all of these packages represent hundreds or thousands of hours more of engineering time that is required to implement this. And so we were able to leverage this software and build on top of it in order to do our advanced reconstruction. And we couldn't have done this at all without these packages being available. So it was very important that the software that we were working with was building upon existing software. Otherwise, we would be writing it all ourselves, and it would take an incredible amount of time, and we wouldn't have been able to do what you see here. So, one of the important things is about FAIR is standardization. So there's a real requirement for consistency in what we do. So if we look at this sort of the text on the right, you can probably tell me what that is. The symbols, the order of the symbols, we won't quite understand, but you can probably tell me that, Homo sapiens is involved. There's AGCTs, so this looks like genetic data. There's a certain length here. And if you knew a little bit about chromosomes, you might even be able to tell me this is chromosome 14. This is part of the Human Genome Project, and I was able to download and extract this data pretty much straight away. It's a kind of mosaic of various genes that are available within humans. And so it's not a single person looking at a kind of composite person here, but that information you can get very, very readily and start interacting with it. And the important part there is I can eyeball that, and the standard is known. It's documented, and there are examples. So in order for findability to be a thing, we need machine readability. And you'll see that in a second for why you need machine readability. But there's a few people using FAIR methods. There's the Human Genome Project that I just listed a second ago. I quite like the high energy physics CERN portal. It has a very sort of Google feel to it. You can punch in, a certain search engine and say, okay, let's look for energy equals 7 teravolts, and then search for that, and you'll get all of the experimental information coming out of the ring, out of the collider, and you'll be able to start analyzing that straight away. There's examples coming from chemistry, the protein data bank stuff, repositories like Chembl, and in medicine there's the virtual human, things like that. There's a lot of examples of where this is pretty key, and a lot of other fields are putting this at the core of their workflows. If I go and look up something from one of these databases, I can say, okay, let's type in some letters here, and look, I've discovered paraxylene is in there, or everyone knows all about paraxylene, and I can pull up all of the information about that. And so this is a fairly simple example, but there's information here related to structure of that, including machine readable structural definitions and things like that. And that's pictures for humans as well. So, what are we doing in terms of trying to make our software fair? So we have made a lot of the work that we do open source and available online. You can download these, feel free to search for them. I mean, we're not the only people doing this by any means. And the sort of dates that I put in here are the dates where we've last had major updates. So, there's visualization software. There's advanced reconstruction for multiphysics. So you too can go back and correct all your reconstructions and make them nice and neat and tidy, and be able to make sensible measurements from them, provided you have some imaging data to back it up with. An important thing for us is being able to reuse the algorithms. And so we've extracted a lot of the algorithms that we use for low-level data processing, things like file I/O, clustering, very, very simple sort of calculations. They've all been put into a library that we call the Probe. We've written POS file scripting systems, so you can do things like simulate crystals, add noise, do rotations, automatic cluster analysis, these sorts of things. So POSGenPy leverages a couple of these layers of software, so both POSGen and the Batten Probe, and that does automated cluster analysis. So it very, very quickly goes through all of your data and pulls out various plots about how clustering works across multiple files. So you just throw all your data in there, give it some information about what you're going to run, and it will pull all that information about you. In terms of equipment, we're providing sort of HV and UHV hardware communication libraries. So tools like LibVacuum device allow you to do machine automation. So not only are you looking at the sort of data processing side of things, we're also looking at equipment. So being able to make sure that you can talk to all the various vendors' pieces of equipment. You have a pressure gauge, you want to be able to make sure you interlock on that. You can do these sorts of things. So, it's a bit of a multi-pronged approach, and there's three key things here that are important for researchers. There's end user tools that enable discovery. So things like being able to go through that map and say, okay, let's pull out some of the automated information and lots of data sets that are similar to mine, and start doing data comparisons across those. This is going to become increasingly important as we move to things like machine learning, which I think has been a little bit slow to pick up in the Verb, but we're seeing more and more of it. Algorithm libraries, they're going to have to require automation. the amount of data that we process today is increasing very dramatically. We need to be able to automate that. And being able to make sure that the algorithms we use are bug-free, so we can have high accuracy tools that do all the right things. That was one of the advantages of leveraging existing open source software, is we didn't have to debug it. The debugging takes a lot of time. And so, we were able to do that. And data repositories is the final thing. We can reuse existing data sets to gain new insights with them. Or if we're not sure about a result, we can go back and satisfy ourselves that, in fact, the result is quite good and is quite valid. And so, as I said, we're not the only ones that are making software available. There are many, many packages available for Atom Probe. And this provides a common base for information exchange, particularly when you're working with people that are not part of your lab or part of Atom Probe lab. A lot of people are coming in from geology fields or coming in from pure metallurgy fields, trying to find out about their piece of equipment. They want to be able to see their data set and interact with it. And so there's a common set of software that you can go and look for, and this covers simulation, visualization, reconstruction, analysis. And if you really like typing long strings into your web browser, that dedicated, you can go and see this spreadsheet that the technical committee is providing that lists all of the software that is available for Atom Probe to use. And so that this is about making it more findable and more reusable. So what are the goals for data sharing? I think one of the key pieces of key takeaways that we should be coming from this is that we're speeding research. We're reducing duplication of effort. We don't need to do entire parameter sweeps for various laser energies, laser powers, or whatever. We can just go and automatically pull that out of the database by looking at neighboring data sets and saying, okay, what would happen if we run virtual experiments across this? If you decide that there is something interesting in there, you can then go and repeat those experiments directly, but you can quickly go and zero in on things that will matter or won't matter by automating this. The goal there is really to maximize automation. And as I said, things like machine learning are helping to be able to analyze these large troves of data in one swoop. So you can quickly say, okay, which are the components of the analyses that matter? The other part is increasing visibility. So, there's a lot of overlap in different research topics. A lot of the work that we did has not just been Atom Probe. We've been pulling in information and methods from places like astronomy, particularly when we're doing statistics and trying to look at the algorithms behind noise levels and these sorts of things. There's been a lot of work done in other fields to be able to create models, and you can reuse these. But another thing is making it more reliable information exchange. Sometimes there are papers that are just not available, or there's data that's not available. It's very difficult, and you might have been pointed to some paper in some country where the person has already moved away from, and that was over 10 years ago, and they're not there anymore. And so these data repositories about making sure that the outputs that we generate have an increased lifetime, so they're increasing reliability within that. And it's also about decreasing our data loss. How many times have we gone to databases and had a look through them and seen that here's sample or my sample A or X final, and the context around all of this is no longer available. So in order to support actual data sharing, I came across a paper that said that no public or standard location or repository currently exists for Atom Probe data. Even though there were efforts by other groups, in this case they're citing the Sydney and Colorado group's work. So that was the CBL, and I forget the name of the other one. Apologies. So these are critical issues that are unaddressed. So I agree that these are critical issues that are yet to be unaddressed, but I'm not certain you actually do need a single repository to do this. So, most of you are using email or visiting web pages. It's not like there is a centralized computer that holds every web page in the world and we all access it. What it is a distributed system, or what we call a federated system, where you connect to the appropriate server that hosts the information you want, and then you pull that down from it. This is something that you will see repeated across lots of different popular systems. Email, you log into your email server, you download it. If you're using software tools like Git or Mercurial or any of these things, what you're doing is you have a distributed repository system, and you go and connect to the server that has the latest copy, and you interact with that server to push and pull information from that. So none of these things are actually single repository systems, where they're a collection of computers working with a common standard that tells you how to access information from each of these servers. And then you just ask from the appropriate server, do you have the piece of information I want? That might be, for example, an Atom Probe data set from a specific group, might be available in various servers throughout the world. So, is this a problem that's too hard, too complex, or too big? People say, oh, Atom Probe data is really big. It's not possible to host this. It's going to be very expensive. There's no way we could do that. But if you're watching Netflix, you're looking at you're using UHD mode. you're looking at about 7 gigabytes per hour that you're pulling down. You know, for an uncompressed atom probe data running 24/7, you're looking at maybe 0.8 gigabytes per hour at best, sort of coming out of that. So it's not like the data rates are out of the range of what's achievable for even a residential or a home computer setup. It's quite accessible. You know, storage, storage, you know, this is typically in the range of 0.4 US dollars per gigabyte, or about, you know, $0.03 per hour. That's significantly less than the cost of the electricity required to run the atom probe. So it's not like this is too much data and we can't possibly store it. It is totally achievable. Too complex, you know, I would agree that there are complexities involved here. So I think one of the key complexities is being able to shift our mindset from we'll make our data available if somebody ever asks for it, to we should be more proactive about the data that we're providing and making sure that it's available, because that can be mined, right, various algorithms, and then information can be extracted from it, and that allows us to do more interesting things, such as we saw, you know, for example, in the deuterium cases. And I don't think there are any sort of technical barriers to implementing this at the moment. There are certainly barriers to it, but I don't think they're technical in nature. So, you know, science is increasingly requiring fair research at the policy level. If you haven't been hearing about it soon, you might hear about it pretty close in the future. And I think we're a little bit behind the curve on fair access. You know, we haven't been proactive about sharing our data and making it available. And I think we're sort of being pushed towards doing that at the policy level. So there are efforts being made, and very good, very important efforts. But at the moment, I don't think there's a clear winner in terms of how we interchange experiment data between labs. I think at the moment, probably the predominant way would be people using email or FTP service or what have you, just sort of interchanging individual data sets at a time. But there's no standard way to be able to see experiments between different labs. And I think this is going to require a bit of effort. It's not something that is free in terms of time, but it is something that has very clear rewards, and we've been able to leverage that. So we've been able to find more information that would not have been available had we not gone through and mined that data. And I think, you know, the key thing was we need more community consensus and a little bit more leadership to be able to say, okay, this is the kind of problems we're having, and in order to overcome it, we just need to be able to make our data a little bit more available. So I hope that that presentation introduced the concept of FAIR and gave you some of the idea of the software and advantages that come from being able to share your research a little bit further. Thank you very much.
Thanks, Dr. Haley. Thanks for your timing. We still have 2 or 3 minutes. We maybe 1 or 2 quick questions. Any questions or comment? Oh, yeah, one comment on the durability. Okay, Christopher. Okay.
Hi, Daniel. Very, very interesting. I have one question. You had quite an optimistic view on the cost of data transfer and data storage. I was wondering a little bit about the examples that you showed, where you basically said, okay, we needed a lot of data in order to look at certain things. That probably was a few dozen or a few hundred data sets from your local thing. If I just think about the average size of a typical atom probe data set, and I wonder if somebody, sort of say, for his own research will download 100 of your data sets from your site, it will probably pose a heavy load on your internet connection. And
no, not really. That you know, 100 data sets, 100 gigabytes. That's not very much. You know, if you look at your camera roll from your Apple iPhone, it's going to be quite a number of gigabytes within that, and you will sync that to the cloud pretty straightforwardly. The data rates used to be in a sort of regime that was inaccessible to a home or lab, but now they're totally within their sort of volumes that we can access. It's because Atom Probe has sort of always been generating data at similar rates. It's increased a little bit, but the technology, you know, a lot of it's coming out of material science, really, to be able to make, you know, more better optical fibers and better platters on your hard drives that have higher storage, higher transfer rates, these sorts of things. And that's, you know, dramatically shot up over the past 10, 20 years by orders of magnitude. And so it now is within a range. You know, you're not going to do that interactively. It's going to be a bit like going to the library. It's going to be like, okay, I want these data sets and I want them tomorrow. And then we'll start doing that. So you'll download to your local server, you'll cache that information, and then you'll be able to interact with that locally within that. But, you know, the hard drive that's sitting on my desk, that can hold 0.5 terabyte. worth of information, which is hundreds of experiments, and that's not that's not exactly a large drive. Multiple terabyte drives are available for $50, maybe $100. It's not an expensive operation to do that, especially when you consider the cost of doing some of these experiments. Particularly the Cerium experiments, quite expensive. The cost of heavy water, it's not cheap. So I think it is in a realm that's accessible, but it's not something where it's going to be interactive and you're going to be pulling the network over the network dynamically. It's going to be something where you pull it down cation and then start interacting with it on your local computer.
Okay, good, thanks.
Okay, I see another hand raising, but due to time limits, we have to move forward. So Marcus, can you contact Dr. Halley after the talk for detailed discussion? So thank you, Halley, again.
Thank you.
Okay, let's welcome our next speaker, Mahapad Manajam from Frederick Alexander University. He will talk about an open source Python package for controlling atom probe tomography environment, experiment, and calibrating data. Mahapada?
Yeah, hi, do you see my screen?
Yes, yes.
Okay. So hello, everybody. Today I want to speak about PyCCAPT, which is an open source Python package for controlling atom probe tomography experiment and also data calibration. Yeah, for many years, scientists have been always looking for ways to get into atomic scale. As you know, atom probe tomography is the only technique that is capable of 3D imaging and do chemical composition measurement at atomic scale. But so far, most of APT works have been done with commercial atom probes, mostly Kamika. There is more or less a monopoly by this company. The commercial atom probe has the limitation of closed instrument hardware and locked-in control software, which means it's not easy to, or in most cases, not possible to upgrade the hardware. And also, we don't know what is really happening within the control algorithm or calibration process. During the last years, we see a huge improvement in bus systems like USB 3 and also runtime. I mean, improvement in runtime speed of high programming, high-level programming language like Python. Especially with these 2 points, we implemented a Python package which is capable of controlled atom probe tomography experiment entirely and also do the calibration and reconstruction. This software was implemented in Python under version 3.9. I mean, for graphical user interface, we used PyQt6, and for plotting, live plotting within the graphical user interface, we use PyQt graph library, and these two libraries, Matplotlib and Plotly, were used for all the plotting and 3D plotting during the calibration process. This package consists of two main modules. One is the calibration and one is control, and all these modules contains a lot of sub-modules, for example, to control the devices or do the calibration or reconstruction process. In this software, we use multiprocessing and multi-threading to parallelize the task and to improve and increase the computational power. And in any time critical functions like reading out the TDC, we use the DLLs and buffering techniques to prevent any missed data. There is some also Jupyter notebook workflows in this software that can be used to analyze the data, calibrate, calculate the propagation delay of the instrument, and so on. This software benefits from logging functionality to drawbacks any errors that could be happen within the experiment, and also there is a JSON file that could be used for enabling and disabling the feature in the graphical user interface, and also specifying the ports for each devices. The pipeline of this software is as following. After inserting and aligning the sample, the software opening the ports to high voltage power supply, voltage or laser pulsar, TDC, and set the starting value. Then the main loop of the experiment will be started. This loop can be adjusted to run between 1 to 50 Hertz by the user. And within the loop, we read the TDC values, calculate the number of detected events, and then relative error to the desired detection rate. And based on that, regulate the high voltage and pulse amplitude or laser power. At the end of each loop, also the software check the termination condition that is set by user, and if any termination condition happens, then all the devices released, and the software close the ports and save the data in HDF5 file format. In this file, there is not only the detector data, the hit position, the time of flight, the high voltage, but also we save the raw data of the TDC, and also some metadata like vacuum level in different parts of the instrument, and also images of the sample during the experiment. This is a screenshot of the graphical user interface after a successful experiment of aluminum. You can see here the pole for aluminum in the heat map of the detector. User can here monitor the experiment, and also here see the statistics during the experiment, control the vacuum level in different parts of the instrument, control the pumps and gates to pull in or pull out the samples, see live images during the experiment, and also setting up the parameters. This is another GUI that was implemented for our laser atom probe. To control the laser intensity, we use these natural density filters. By rotating these filters, you can increase or decrease the intensity of your laser, and as a rotation motor, we use this rotation stage from TeorLab. Here there is a possibility to fix the angle of the ND filters to a fixed value, or increase this step by step after detecting, for example, 50,000 ions in this case. The first step to do the calibration is calculate the T0 of your instrument. That is because of delay in electronics and also all the cables that you use. So to do so, you should measure a known sample, and preferably a single isotope sample like aluminum and cobalt. Then crop your data set, especially to the center of the detector, calculate the mass to charge, and then you can since you know all the mass to charge values for all the peaks for this sample, it's a known sample, so you can reformulate the above formula and do the linear regression. Then the position that this line hit the vertical axis would be your T0 for the instrument. For this process, we have a workflow that can be easily follow up by the user and calculate the T0 of any instrument. Here, I just want to show how the process of the voltage and ball correction happened within this package. This is a time of flight of aluminum sample. This is a time of flight histogram. It's uncalibrated. If you pick all the ions for the highest peak, you see that ions travel faster and faster by increasing the voltage. And during the voltage correction, we want to fix this. Ideally, we should see a line. We should see a single value for all the ions, single time of flight. So this is our voltage correction factor that is multiplied by all the ions within our data set. And then we can see that we more or less fix the problem of the voltage in our data. The next step would be the ball correction. As I said, here we should not see a tape, we should more or less see a single line. So we apply our ball correction factor to the data, and then we decrease the width of this tape, and we are closer to our target. We iterate this process until we see no improvement in the MRP, and here we can see a huge improvement in the time of flight MRP that we calculate. In this slide, I want to compare the results of our Oxide titanium voltage atom probe with LEAP 5000 XX direct flight test which is located at Düsseldorf. These two experiments were done on the pure aluminum, and here you can see the overlap of the two mass spectrum. As you can see, there is no big difference between these two instruments, during the calibration process, except the part that we see low amount of hydrogen in the Oxide titanium atom probe, which is one of the main feature of this instrument. In summary, we saw the features of PI-CC-APT as a software to control the atom probe experiment. This software is modular, so it's easy to add any new package to that. I mean, any new TDC. So far, we test this software for two types of TDC. One of them is from Surface Concept, and the other from Browntech. So, but it's easy to add any new module, for example, for new TDC to this software and expand the coverness for different TDC. In the calibration part, we have the ROI selection that can be used to temporally or especially crop the data sets. As I said and showed, calculate the propagation delay of the instrument, do the voltage and ball correction, and also 3D reconstruction. Now it's also possible to load and work the ePose, pose and range file from Kamika series to compare the results between your commercial atom probe or with your in-house atom probe that you implemented. This is a Jupyter notebook files for 3D reconstruction. As you can see, user can here select the model of the TDC, the data set name, flight path, and T0. And for example, this is reconstruction results of stainless steel that I did with this workflow. This project is publicly available under this link on my GitHub repository. You can use this QR code to directly go there and see the features and how you can use this software. In the end, I want to thank all the people that helped me during this project, and thank you for your attention. I'd be happy to answer your questions.
Okay, thank you, Mohammed. Thank you for your time. We still have 3 minutes. Maybe one or two quick questions or comments. Any questions?
How did you estimate the ball in your ball correction?
I try to fit hemisphere on the detector. I mean, on our XY position that I have on my data sets.
Okay.
So there is more or less like what is happening in the LEAP reconstruction process based on the Larson book.
Yes. Okay. Yeah. There might be better ways. Can maybe discuss that separately. Thanks.
Yeah, you're welcome.
Okay. Any more questions? So if not, let's thank Mohammed again. Let's welcome our next speaker, James Douglas from Imperial College London, who talk about gas injection system, pre-cryogenic atom probe tomography, sample preparation. So welcome, James.
Hello, thank you. Can you hear me okay?
Yes.
Fantastic. And you can see my screen?
Yes.
Yes, fantastic. Thank you. Yes, I'm James from Imperial College London. I'll be talking about cryogenic sample preparation. And this is some of the work that we've done at the new Imperial Center for Cryomicroscopy of Materials. There we go. So why do we want to do cryogenic sample preparation for atom probe? Well, we want to reduce sample damage. So if we want to reduce the effect of gallium diffusion into, say, aluminium alloys or hydride formation in zirconium or titanium alloys or metals, we can do that. We may want to be able to fix the location of mobile species like hydrogen or deuterium. We can do this in bulk metal samples. We can do it in a non-site specific manner. And we can see it in this paper over here. And we can do it for liquids and soft matter. And this is what we're particularly interested in our new facility. And for this sort of thing, we do need to do cryogenic sample preparation, and we need to be able to do site-specific sample preparation. So generally, this will require focused ion beam lift out at cryogenic temperatures. Cool. So why is it challenging? So we need to have a method of making our stage cool. Depending on the instrumentation you have, the more modern systems are a bit more flexible. But if you are retrofitting your focused ion beam, you may need to include cooling braids. You may need to add in extra bits and pieces. All of these can break. And if you want to have cryogenic transfer in and out of your system, then you might need like a vacuum cryo transfer module like this one from Ferrovac that we have over here, or your own setup. But once you've got it into your sample chamber and you've cooled it down, the milling is relatively straightforward, and it's pretty much the same. And you can just warm it back up again if you want to, and then just take the sample out if you don't need to have cryo transfer. However, if you want to do a cryo lift out, you need to have a cryogenic manipulator, and you'll need to have a method of adhesion suitable for cryogenic temperatures. Now, this is the key part. So most of the time when we do a fib lift out, we will use a gas injection system to do site-specific decomposition. We'll put a gas into the chamber, we'll decompose it where we want to build up a solid material. And then we get a metal-enriched region within a carbon matrix, and you can get different metals, different precursor gases, this sort of thing. But what happens at cryo temperatures is, as I'm sure many of you are now aware, it condenses everywhere, and this can pose a bit of a problem. So it's not so much of an issue for the actual lift out, as long as you control the thickness of the gas that you've condensed. As in this example over here, we can still lift something out, but the gas goes everywhere. And if we want to turn it into a solid conducting material, we then have to cure it, as it's often called, by using secondary electrons from an ion beam or electron beam in the same way that you would normally do for a focused ion beam deposition. So that's okay. But can we actually just use that process and be able to make it suitable for mounting our atom probe samples? So not really that easily. As in, here's just a picture of a standard silicon post that I've cut a little wedge out of, so we can sort of simulate what it looks like if you had a open space from a lift out wedge. And if you then open your gas valve, condense gas everywhere, it does fill in the gap, but it doesn't fill it in completely uniformly, and it's difficult to cure to make into a solid conducting layer, and that's quite key. This methodology does work, as this paper from Schreiber et al. Back in 2018 showed. You can use redeposition to be able to pick up your lift out lamella from your substrate. This is done by just milling very thin lines next to the manipulator and the lift out bar. Sufficient material will then back sputter, and then we'll be able to make a reasonably tenuous connection, but it's good enough to pick up. Then you can mount that onto a pre-prepared post. Here we can see that it's been cut at an angle, and then you can mount it using redeposition and then try and fill in the gap on the side to give a better connection using gas injection material, and then try and cure it. It's viable, but you haven't really optimized the electrical, thermal, and mechanical stability from this. So can we improve it? So can we avoid using the GIS? Well, there's a large amount of work in the TEM community of just using on-grid thinning. So this just allows us to have our sample on the grid itself that we have put into the focused ion beam, and then we can just coat that with a thin layer of cryogenically condensed precursor gas. We can then cure that where we want it to be, and we can just thin on the grid. We can just make our samples as is, no lift out required. Similarly, there's a lot of work on satellite dish preparation using plasma fib, where you can make your sample on your substrate. Similar idea to TEM on-grid thinning, where you don't have to do any lift out. However, if you want to do fib lift out and you need to do it, say, for example, complementary cryo TEM and atom probe, which is something we're looking forward to doing, well, looking forward and looking at the challenges for it, how do we do it? And one methodology is to think about redeposition. So in this paper over here, the authors wanted to fill in cracks in their TEM lamella from a cracked sample, such that it didn't bend and twist when they were doing the final thinning. And what they were able to do was have a piece of platinum material they had deposited right next to the TEM lamella, and they back sputtered material from that into the cracks in their TEM lamella. So they were able to have a localized sputtering source that would fill in a gap. That sounds very much like what we want to be able to do. So in this case, they use platinum compound rather than the sample itself. And that's a key thing as well, because the sample will often be, if you're doing it, say, a frozen liquid, you're back sputtering, say, frozen water as a glue section, and it doesn't really give the good thermal conductivity. So what do we need to do for atom probe? So the glue, as it were, we need to connect our sample to our support structure. It needs to have these parameters. And here's just an example of a piece of steel that has been glued down using tungsten compound. We can see the nice cross section here, the silicon post, the high atomic number tungsten, and then this it's a magnetic steel here. We can see the different microstructure, all cool. But you can see the region we need to deposit into. It's got quite a small area that we need to get right into the cracks of it to be able to fill it in and give a good connection. So generally, we want something that's highly conductive and it sticks to both the material and the support. So sputter coating would be great, and but it's not necessarily that feasible for inside a cryo instrument. You do need to be able to do rotation and tilt when you do your sputtering to make sure you can fill in all the gaps properly. There is sputter coating available on various systems attached to cryo instruments. This is often an antechamber, and you can also get insertable sputter heads. However, you don't necessarily get the rotation and tilt, and you don't necessarily get site-specific deposition. It'll still go everywhere because sputter coating will do that. So you could plausibly make a pre-deposited platinum structure or something next to where you're planning to mount your sample before you cool it down, but it's not necessarily going to be that flexible, as in you're reasonably stuck where that's going to be, and you can't do it when it's at cryo because it'll just deposit everywhere. So we need a local source of conductive material that can be moved and controlled inside the fib at cryo temperatures. Cool. And most modern fib SEMs have one of these already in the form of the micromanipulator. So we have a electropolished tungsten needle that we can put into our system that can be cryogenically cooled, and we can place it, as long as you have good stability, you can place that pretty much anywhere you want in the field of view in the center of your chamber, and you can move it and position it with nanoscale accuracy. This is what we want. And as with all good ideas, you find out that someone had a thought of it over 10 years ago. And in this paper here, it wasn't used for gluing down samples. Instead, it was used to be able to try and coat the edges of an already made atom probe tip. So a piece of metal was picked up using a micromanipulator, and then it was sputtered onto that pre-sharpened thing. The idea for using for gluing wasn't necessarily there. So the question is, can we use a tungsten micromanipulator to act as a local sputtering source and do a full lift out? And we're just going to demonstrate how we were able to do that. So for this demo, we've just used a single silicon coupon with flat top posts in a standard puck. This is into our cryo stage, the equivalent stage we have on our plasma fib. And we did this for ease because it's a standard material. Everyone knows the silicon that we have for the coupons. And we also have a piece of flat material and a support structure next to each other. So we can make a sample from the flat piece and put it onto the support structure without having to mess around with changing samples. So this is the details of the instrument we have in Imperial College. We use xenon plasma. We mounted our clip and our coupon in a puck, cooled it down to -180 degrees. And then we're able to prep our posts in situ as with the Schreiber paper. And we cooled down a manipulator, and we just milled out a standard piece of silicon and lifted out using redeposition, again, like the Schreiber paper. This is what it looks like. You can see the little lines on the edges of the manipulator. And then we mounted it on the post. We found that because the adhesion between the post and the manipulator wasn't great, we have to be able to be very careful to place it down in a single motion. Otherwise, as soon as you try and lift it back up again, it starts pivoting. So you have one go at this, but it's okay as long as you have good stability. Then we have, mounting. Oh, there we go. Then once we chop off our manipulator, then we rotate by 90 degrees. We put, again, redeposition again on all the sides. This is only to keep it in place for the next stage, because this is what it looks like if you just do redeposition on each side and then try and sharpen it. You get the pointy tip, but you don't get a good connection with the substrate, and you have a big gap in the middle. So we want to be able to fill in the gap in between, and we need to fill it in to maximize the electrical, thermal, and mechanical contact. Cool. So we cut our section from the side of the wedge, making sure our region of interest, if we had one, here it's just bulk, but if you had a grain boundary or something, you could have that. And then we cut out a section on the side, and we place our manipulator as close as we can get into that cutout of that region there. Then we do a single pass mill going from the gap onto the manipulator to try and sputter material into that gap. And then once we cut off that material, then we move the manipulator back in. and then we put more material in, and keep on doing that back and forth until we filled in as much of the gap as we need to make sure there's a single continuous line all the way through from the top to the bottom through our region of interest. Took about 10 minutes for this. Cool. Then we sharpen it. We can rotate it if we want to and put in more material. We sharpened it using standard annealing emitting low kV polishing. You can see a bit of contrast variation in the tungsten, so there's a bit of microstructure. It's not completely homogeneous in structure. And then we warmed up the stage, and then we took it out, put it into our LEAP 5000 XR. We didn't need to do a vacuum or cryo transfer, so we just didn't. So we then did laser pulsing with these conditions and then voltage pulsing on it. We want to compare them to standard PSMs, so we ran the PSMs as well in the same conditions. If we look at the laser pulsing, we can see that we have pretty much exactly the same mass spec and thermal tails as we did for the PSMs. And then we did voltage pulsing, and they look pretty much exactly the same as the PSMs. And then the hit maps look pretty much exactly the same as the PSMs, apart from we have a slight offset in the pole because we did a lift out, so the orientation is not quite the same as on the single crystal. And it shows that we have good thermal conductivity, electrical conductivity, and mechanical stability, because we went up to 9 kV base voltage with the voltage pulsing, and it didn't fracture. In fact, it stopped. I took an image of the tip at the end. So now to summarize, we're able to use a gas injection-free lift out of silicon at full cryogenic conditions using the Easy Lift manipulator for site-specific redeposition. We can collect data from this tip in voltage and laser pulsing, and it didn't show any significant variation from the pre-sharpened microtips. And we showed it's reproducible. We've done it a fair few times now. We've now done it on materials not silicon, but are actually environmentally sensitive. And this shows that we can potentially have a methodology for doing cryo lift out without using the GIS for multiple different samples that require this sort of preparation. So I'll just leave it there and say thank you.
Okay, thank you, James. We still have 4 minutes. Any comments or questions? Okay. Okay, Dr. Harley. Can you hear me? Or Christopher?
Oh, sorry, there's 2 questions I could see as well. Is Dan asked a question?
No, I haven't asked a question. That was
oh, sorry. Yes. Oh, there's one from Devon in the chat. Is it also practical with gallium fib? Can't see why not. As in, as long as everything's at cryo. And there was a question from Nikita Polin. Does the lamella fall off without platinum often? Falls off more often. You have to be quite careful when picking it up. That's the main thing. So the main loss from this was when we were picking it up from the redeposition, and mainly when we were mounting it onto the post. And if you make any sort of vibration when it's being mounted, then that can fall off, especially like changing the aperture in your fib, if you're able to, because that often causes vibration. But that was the main part, that was the main sample. Don't read up and heat up the sample. Now that's a good point. We wouldn't be able to check that unless we'd be able to, don't the redeposit ions have a high energy and heat up the sample? That's something we can check. So this is just to see, can we mount this? We'd have to be able to, if we did it on a material where we could tell if it had gone through a heat change, then that would be possible. That's a very good point. Thank you.
So James, there is also another question from Lisa. He asked, don't the deposited iron have high energy and heat up the sample?
Yes, as I was just saying, I hadn't actually considered that. That does make sense. I'd be more worried about the tails from the xenon beam than the redeposited ions. So the thing to think about would be if we're doing normal sputtering from a sputter coater, that has been shown to be viable onto atom probe samples. But I don't know whether anyone's done that onto frozen things. I think, yeah, as I was saying, I think we'd have to do it on a material where we could tell if it had heated up. So maybe if we go from like vitreous or crystalline ice or something like this could be useful. But that's something definitely to consider. Thank you.
Okay. So let's thank James again.
Thank you very much.
And let's welcome our last speaker, Jean-Baptiste Mallet from DPM Zone. He will talk about, this is his title. So please, Jean.
Do you hear me?
Yes, but can you be a little bit louder?
Okay, like this is correct?
Yes, this is very okay.
So hello, my name is Jean-Baptiste. So I'm PhD student. I'm starting my second year. I am starting my second year. My thesis is directed by Vurpio François, and I talk to you today about a new method for in situ implantation and characterization of hydrogen in atom probe tomography. So for the context, we know the hydrogen is an energy vector for the future. As we can see here with the article on the Airbus project called Day3, you want to decarbonize all airliner for 2050 with a hydrogen combustion system. We know too it's possible to store the hydrogen in solid state, and we know the hydrogen can be unbrittle materials when you go in defect, such as vacancy, interstitial seat, grain boundaries, or dislocation. As we can see here with the APT image, with a particular wheel localization on grain boundary or dislocation with a deuterium analysis. So we need to understand the mechanism at the atomic scale. So as we can see here in this figure, I can, yes, as we can see here in this figure, we need to understand the mechanism at the atomic scale. So the APT appear as the ideal instrument, but need a complex experimental protocol because hydrogen, we know you have a low mass, high diffusion in materials, and can exist in residual gas in chamber analysis. So what's the method to study the hydrogen in APT? Currently, we have two setups in literature. We have cryotransfer. The basic idea is to load in hydrogen with a cryofib, then use a cryotransfer to transfer to chamber analysis. And the second setup can exist is to have a cell connected to the chamber analysis where we can load our sample with a high pressure and temperature. And then the goal will be to decrease as quickly as possible the temperature for transfer to chamber analysis. I write here we have the temperature. We decrease the temperature to 500 Kelvin to 70 Kelvin in 3 minutes. So the question is, another way can exist. Before talk about implantation in situ, quick reminder about the principle of atom probe tomography. So the basic idea is to have a tip with a curvature radius around 15 nanometer, and we apply a constant voltage with a pulse, and the atom at the maximum of the pulse, atoms are ionized and evaporated to reach the detection system. And for this equation, we can get a mass spectrum with the time of flight of each particle, and we can get a 3D reconstruction image. So the implantation in situ, regarding the implantation in situ, we can take the basic idea of Dudka in 2030. The basic idea is to apply a negative constant voltage with this value for this case to generate an electron emission. This electron emission that ionize the environment gas, here is helium, and the ions created will be attracted to the tip with energy. So the electron emission follows this equation, follow Nordheim. This work is good, but there are limits. This is the limits. There are current density limit. For example, for tungsten, we have a 10 power 12 ampere per meter square current density limit, and this limit finally limits the constant negative voltage that can be applied. So limit the implantation energy of helium ions. Here is article is around 130, 140 electron volt of implantation. And as we can see here in the film image, we have a small defect like a seat, interstitial seat, after 7 evaporated layers in tungsten. So this technique is good, but only for low implantation energy, few implanted layer, and limited by the current density of the material. So the new method called pulsed in situ implantation is to replace the constant by a pulse. So we can apply a negative pulse voltage for generate an electron emission, environment gas ionization, and ions attracted to the tip. Here, in my case, is hydrogen ions. We can simulate it with Lorentz. So I can simulate my pulse, simulate my tip, my electric field, and we can extract the energy of my implantation with the tip distance of ionization with different amplitude of my pulse. For example, here I take -1 keV of my pulse. So we have energy of implantation here. With SRIM, we have depth implantation. So we can extract the depth implantation expected. And here we have, for example, if we apply -1 keV, we have an average energy of implantation around 250 electron volt, and the majority of ions implanted are stuck at 4 nanometers of depth. We can compare these two methods, pulsed and continuous, in their limit. So the limit of continuous is -500 volt and pulsed -3 kV. And we have more higher of implantation in the pulsed implantation. To the right of the slide, we have a film image. I do an experience with a tungsten tip to compare the Dudka experience, and I implanted the hydrogen, and I create more defect, more deeper. As we can see here, beyond 36 evaporated layer in tungsten for compared to Dudka. So this technique is really, really good, and we can get an experimental protocol for APT. So the basic is to evaporate my tip just to develop it, turn off analysis, allow gas enter to the chamber like hydrogen. We can apply a negative pulse. We can choose the amplitude, the frequency, the time, wait for a good vacuum, and we can analyze our sample with hydrogen implantation, with hydrogen implanted, sorry. So the result, for example, -1 keV with 10 kilohertz of frequency during 30 seconds with this partial pressure. We have a nickel with a really good hydrogen implanted here. We can get a mass spectrum. As we can see, we have probably nickel hydride. We have a good resolution of atomic layer of my nickel, and as we can see here, we have a good behavior, a really good behavior of implantation for hydrogen for a peak at 1 Dalton. So this implantation is really good, and yes, you can see the implantation is reach 50 nanometer of depth. If we want to study the dose, we can increase the time. So we fixed -1 keV, 10 kilohertz, and we can increase the time 30 seconds, 1, 2, 4, 6 minutes. And we have a reference. That means just basically an analyze basic without implantation. And we can tell the implantation dose is not linear with the time, because if we apply 30 seconds, if we implant during 30 seconds and 1 minute or 4 minutes is not increased. The dose not increase with the time. We are some case consistent with theory, because 30 seconds and 4 minutes, so the blue curve and red curve have the majority of ion implanted at almost 4 nanometer of depth. So it's really good, but some cases are in some cases we have less depth with theory. We have a good distinction between hydrogen implanted and hydrogen come from chamber. So implanted, like for example, green curve, come from chamber is red curve. So good distinction between these two behavior. The implantation is really strong. We can see here we have 50–60% of my tip is hydrogen here, and beyond 8 minutes, not 8 minutes here, because my tip is completely destroyed. So the implantation depends on the other parameter. So the first problem is about the damaged tip. We can create more defect at the surface. We can destroy the surface. So the question is, what is the real implantation depth? Because if we destroy my apex, if we destroy my apex, the depth, what is the real depth? The second point is about the reproducibility and comparison. Because I do some simulation and I see I see the influence of the curvature radius and shock angle about the electric field, so about the electron emission and about the implantation. So the implantation energy and dose can change if my tip shape change. And for experiments, the best way is to do a multiple implantation in the same sample. Before I not did that for multiple reasons. Currently, I do that. And another way, it's the same way, is to do a flip preparation to standardize the tip shape for make a lot of tip with the same tip shape for a better comparison. So the question is, what is the better comparison? So for conclusion and perspective, we have high concentration for depth range around 10 nanometers. So here we have hydrogen beyond 40% concentration. Preceding implantation is can have a higher energy that continues. And perspective, currently I try a new implantation with deuterium. Heater installation for heat treatment to distinguish to a good distinction between diffusible and deeply trapped hydrogen, and new study with new materials with zirconium or scandium precipitate, as we can see here, this precipitate with hydrogen around this precipitate. So thank you for listening to me.
Can I ask a question?
Yeah.
Well, are you limited to hydrogen or helium, or can you actually try to implant other gases?
Actually, currently we add a RAM gas with two gas, only two gas, only deuterium and hydrogen. But if it's necessary, we can add another gas in future.
Okay, thank you.
Maybe I quickly ask another question about another gases. So do you think of maybe implanting in the future something like a precursor gas? I think if you think further about this idea, you could use something like what we use also in the FIP, this platinum precursor. Then you could put platinum inside, and with all other precursors, you could maybe in the atom probe put any kind of atoms into your sample.
I don't understand your question.
It's not a question. It's more of an idea, more of a comment that one could maybe, with your approach, implant any kind of defects you want into every material.
Yes.
So maybe the only limitations I think of the precursor, it's usually have in the platinum, it has some additional groups. So these groups have to go somewhere. This I don't know how to handle this because there's a carbide. So it's something with yeah. So maybe you have idea on that.
Yes, I know this this work is really nice for the future, but it's difficult to understand the good way sometimes for a good study, you know.
Yes, Thank you.
Okay. So if no more any question, let's thank Jin again.
Okay, thank you.
Okay. So next we'll go to our second post session. In this post session, we have totally around 11 post presenter. Each one will have 4 minutes to introduce your poster. So let's welcome our first post presenter, Huan Meng.
Okay, thank you. So I'm sharing my screen now.
Okay, Jin, can you stop your screen sharing? Jin, can you stop your screen sharing?
Jean-Baptiste, il faut que tu arrêtes de partager.
Je sais, j'ai un souci. J'ai fait une connerie. Là.
Sors un gros marteau et pète tout.
Merci, c'est bon, je m'en suis sorti.
No problem. Yeah.
Okay.
Okay, so, oops. So I need to put into starting mode. Okay. So can everybody can see the full screen?
Yes.
Okay, great, thank you. Welcome to my poster called Structural Visualization of Ordered Mesoporous Silica using Atom Probe Tomography. My name is Huan Meng from University of Stuttgart. The ultimate goal of my work is that one day we hope we could see that how the heterogeneous catalysts is anchored in the very well-defined ordered mesoporous material system via some linkers to study about molecular heterogeneous catalysis under confinement effect. And the first step is to visualize the porous material scaffolds. The strategy is to fill the pores. As you may know that the hypothesis of the current mainstream reconstruction algorithm is based on that only one hemisphere is being evaporated at one time. So here in this poster, I presented you about ordered mesoporous silica filled with 2 different polymers. One is CDAP, and which is the surfactant already existing in the synthesis route before calcination. And the second is the cross-linked DCPD. And the purpose is to compare about the results from filled with CDAP case. So experimental procedure is we adopted normal FIB lift-out procedures, then shaped with FIB cryo technique and measure with an atom probe. And then on the right side first shows you the mass spectrum of the case of ordered mesoporous silica filled with CDAP. And as you could see that the tips mainly consist of typical CDAP peaks labeled in 4 orange boxes, plus 5 typical silica peaks labeled in green boxes. These peaks also appeared in the pure bulk silica and the pure CDAP peak measurement. And then further to identify that our peak assignment is plausible, that we calculate that we found the chemical stoichiometry is similar to the theoretical values in both substances. So tip have been assigned and then be reconstructed, but unfortunately we could not really see the pores due to the fact that pores are really small. The lattice parameter of ordered mesoporous silica is about 4.4 nanometers. So one extra step has been added, which is based on the neighboring analysis. Local density map has been created, and on the down left box, you could see 1 vertical slice with 5 horizontal cross sections of the measurement. You could roughly see that the structure is porous, but it's not so regular. So we assume that the reason might be the evaporation field difference between the silica and the CDAP might be too big. So in order to smear out, to bring them together, that we try to fill later with the cross-linked polymer DCPD. And in this case, you could see that in the picture in the middle, down, and we got better resemblance about the atom probe study compared to the TM pictures from similar pore orientations. But in both cases, we have observed that the high density area, these red lines, are mostly contributed from the pores, whilst low density area are mostly from the walls, due to the observation that in the red region where the composition of the carbon and hydrogen mainly exists, while the silicon and oxygen mainly exist in the white and blueless low density areas, which reveals that the local magnification effect still exists, also explains why the picture we got still has some distance compared to the TM image. But to further explain this incomplete story, quantitatively, we will use the Tabsin simulation, and we will use the bitter filling and the different porous material to bring the evaporation difference smaller. And this is all I want to present. Thank you very much.
Okay, thank you, Kwan. Okay, let's come to our next host presenter, Oscar Albert.
Yeah, thank you. Okay, nice. Can everyone see the screen? Yep.
Yes.
Okay, well, thank you. Hello, everyone. I'm Oscar Lopez, and I will introduce you briefly to our ongoing research on molybdenum disulfide and molybdenum diselenide heterojunctions. Well, these materials are semiconductors and have potential applications in photoelectronics, thanks to the possibility of tuning their electronic structure and enhancing electrical performance. For example, energy harvesting devices, photocathodes, and photodetectors could integrate these materials with reduced dimensionality and improve conversion efficiencies. But putting these materials into heterojunction arrangements will remain a fundamental challenge for further implementation in such solid-state devices. But this is a very exciting topic in material science. Precisely, our research targets the aspects of this particular interface and the information of such. And for this, we started with radio frequency spotted MOS2 and MOS-E2 on top of silicon oxide substrate. We found a dependency between crystallinity and thickness. The 500 nanometers heterojunction shows the best quality in terms of crystallinity compared to the thinner and the thicker samples, 300 nanometers and 600 nanometers, respectively. Then further characterization by Raman and SEM confirmed this, but at this point, we still lack of a detailed description of the interface, although we know that both materials are present distinctly in the interface. And for that, we decided to try atom-proof tomography on this heterojunction, which has resulted in a challenge. APT is not a standard technique for such materials. We know these materials are layered semiconductors and highly sensitive to beam radiation. But as APT is being used to examine nanoparticles and biomaterials with atomic resolution, we decided to go in this direction. We did APT measurements previously, but on molybdenum disulfide, and indium zinc oxide interface. Those measurements were successfully, we reported them, but now the stability of the heterojunction, the stability of these arrangements between molybdenum disulfide and molybdenum diselenide, it's the biggest case here, because under the measurement conditions, the interface is not stable. We have an early fracture of the tip and less than 1 million hits, but we are still in the process of improving the APT measurements of its heterojunction, but orientating the interface with respect to the tip. Finally, we can say that this MOS2, MOS-E2 heterojunction are achievable by radio frequency sputtering. The heterojunction shows a dependency. The sample with 500 nanometers presents a higher degree of crystallinity compared to the other samples. And the atomic resolution of this sample by APT presents a challenge due to the nature of the MOS2 and MOS-E2 under high radiation, but this is an excellent research opportunity for these materials. And thank you for listening. And if you have any comments, suggestions, or questions about this, feel free to contact me. And thank you very much.
Okay, thank you, Oscar.
You're welcome.
Let's welcome our next post presenter, Jonas Weld. Are you there?
Yes, hello.
Okay.
I share my screen.
Mm-hmm.
So should be visible right now.
Not yet. Oh, there. Now we can see it.
Okay, you can see it. Perfect. I was worried for a second. So welcome to my short poster presentation about my current ongoing PhD project, and it's about the fractal grain boundary regions grown from nanocrystalline palladium gold. And to give a little bit of a background, typically in heat treating metals, we would expect from the microstructure smooth grain boundaries and a unimodal grain size distribution, meaning same size grains about. Now in palladium gold, prepared by IGC methods, we get a whole different pictures. As you can see here on the left, is an EBSD picture of such a sample that has been heat treated after being manufactured by inert gas condensation. This shows big grains with irregular grain boundaries embedded in a nanocrystalline matrix. So there's a lot of the matrix that's still nanocrystalline, but we also have huge grains and we don't have smooth regular grain boundaries. This is work primarily done by Karl Grill and his group, and now my project focuses on looking at this under an APT angle. So we are trying to answer first off if there are any features, mainly compositional features, in the region of these grain boundaries that could elucidate this phenomenon of this abnormal grain growth and these irregular boundaries. For this purpose, we have used samples that were priorly prepared for these studies and lifted out certain parts on these boundary regions and prepared IGC and arc melted tips. So the arc melted is a reference point and the IGC is obviously the really interesting part. So first and foremost, we were really surprised that we had lots and lots of contamination. Like there's carbon, there's oxygen, there's silicon, and there's molybdenum, and there shouldn't be any of these things. But since this is the material that shows this behavior, this could also be a big opportunity. As you can see, the arc melted sample shows a regular picture. If you look at the grain boundary here, you see some segregation of phosphorus and some silicon, as you can see on this profile as well. But the IGC sample shows, after a cluster search, 3 different distinct clusters that show low overlap. So there's carbon clusters, oxygen clusters, and silicon clusters. And these divide the sample along this, what we think is the grain boundary, which in itself doesn't show any segregation whatsoever. The project is still in its early steps and stages, but this is a really promising result. And we will now be looking into where this contamination is coming from. And furthermore, if this is really what is the reason for this behavior in the grain growth. Thank you.
Okay, thank you, Jonas. Let's welcome our next poster presenter, Mohit. Okay. Okay.
Sorry,
okay,
I'm today here, so I'll present it. Can you hear me?
Yes.
Yes, okay. So I will present my poster, which is called Fingerprints Indicating Superior Properties of Grain Boundaries by Correlative Microscopy. And so this work was motivated by the fact that the CRJ solar cell, which are very famous within Germany, they are characterized by an absorber which contains a lower content of copper, and this is called copper poor conditions. But under these conditions, a lot of defects are present in this absorber, And it's believed also that these defects may increase the recombination activity inside the entire devices and then lower the efficiency. Therefore, the researcher had looked to work under copper-rich conditions, because in this case we had much less defects, and of course we reduced the recombination activity. But all the efforts were for nothing, because basically all the devices prepared at copper-rich condition show much less efficiency than copper-poor condition. And the question was, of course, why, and what are actually the fingerprints of the grain boundaries inside these absorber layers. And to answer this question, we have developed and employed a unique correlative microscopy method, which is given by the combination of the EBIC, electron beam induced current setup, with the EBSD and the atom probe. And since we are here within the atom probe community, I thought it would be nice to kind of shortly present how the EBIC is working. So this is inserted within the SEM machine. So we inject electrons inside the material, and the electron injected are going to be collected at external circuit as a current. And basically, when we have a bright contrast in the image, means that mostly all the injected electrons are going to be collected at the external circuit. And if we get a dark contrast, for example, this EBIC image, it means that some of these electrons are going to be recombined with some of the effects present inside the material. So it basically gives us a 2D map where the recombination activity is increased inside our material. And the next step was, of course, to be able to develop a methodology which allows exactly the same grain boundary to be investigated by EBIC, EBSD, and atom probe. And of course, this is a challenge, but it was very successful. So basically, we have an EBSD image. We know where the grain boundary is, what is the character of the grain boundary. And then we have the EBIC image. We see, for example, here we have a dark contrast at a specific location of this grain boundary. Then we lift out this grain boundary, and then we put on a molybdenum support tip. We prepare an atom probe tip, and we see nicely here that we have by TKD, we see the position of the grain boundary, and with the atom probe, we see the location of the grain boundary, which is decorated by the sodium. So with this methodology, we were able actually to investigate the grain boundaries in these two different types of absorber, inside the copper-rich absorber and copper-poor. So already from the EBIC, we know that there are differences between these two absorbers. The grain boundaries in the copper-rich conditions show no contrast change with the grain interior, while for the copper-poor condition, we see that all the grain boundaries here are much brighter than the neighboring grains. So which means that we have a preferential electron collection at the grain boundaries. So this behaves basically like a p-n junction. So we can already say from the EBIC that the copper-poor absorber contains electrically beneficial grain boundary. Although for the copper-rich absorber, the grain boundary doesn't look like to be that beneficial. Indeed, they are basically detrimental for the electron collection. And from that, we have also looked what are the changes in terms of composition from the atom probe. And we have compared the changes in composition in the copper-rich absorber and copper-poor. And we basically see that in the copper-rich absorber, all the grain boundaries has a copper-rich effect or behavior, and indium depletion or gallium depletion and selenium depletion and a slight sodium enrichment. Well, for the copper-poor,
1 minute left.
Yeah, for the copper-poor absorber, we have the opposite. We have the copper depletion, indium, sometimes indium or gallium enrichment, and slightly selenium enrichment, and a strong sodium accumulation. So we have a very different strong contrast between this copper-rich and copper-poor, and we have also done a lot of statistics to see what are the copper changes, the selenium changes, indium changes, and gallium changing based upon these two different types of absorber. And this is actually our graph, which summarizes all our results, which shows clearly that electrical detrimental grain boundary in the EBIC shows a delta beta factor, which is positive. A delta beta factor is basically the difference between the copper changes and selenium, indium, and gallium changes. And in opposite, the electrically beneficial grain boundary has a delta beta factor, which is negative, but a positive EBIC change. So then we have discovered the fingerprints for superior properties of the grain boundary, which are the negative copper factor and a very high sodium content, way superior than 1.5 atomic percent. So with that, we could answer for the answer for the community that not only the copper poor grain copper poor absorber layer are much better because they have this grain boundary with superior properties, but also that the efforts of obtaining a better efficiency under copper-rich condition will be actually impossible due to the properties or bad properties of the grain boundary. And this work had been accepted very recently on, at Advanced Material paper, which we're very happy about that, of course. And it was definitely also very beneficial for the community. Thank you very much.
Okay, thank you, Anna. Let's welcome our next poster friend. Mona cannot come this time, so we move to Turban Bo. Are you there? Turban Bo.
Klaus, it's your turn. There.
Okay. It's
okay. Good afternoon, everyone.
Okay, Klaus.
Welcome to my presentation, Voxelization of Conductivity Characters. My name is Klaus Heisig. What is the motivation? Does fossilization change elemental composition and distribution of these? Our study is about a fossil aqueous chart and a recent stingray. We used atom probe tomography to check it. The fossil is about 250 million years old and comes from southwest Germany. We took specimen from the outer layer of the tooth, the so-called intermetallic layer. What do we expect? We expect to see material exchange during the phosphatic fossilization. Both animals have the same nutcracker dentition. That means they have the same hard shell diet. They live both in a shallow marine environment. They are not closer systematically related. You can see it on the lower left side. Now the measurements. Here we have the mass spectra above the fossilized tooth, below the recent one. It is surprising that they are very similar on the first look. Must work on it to make differences visible. Here's the element distribution. In both samples we found magnesium, soda, and calcium. Interesting. We found clusters of these materials only in the fossil tooth. We interpret this as a segregation at grain boundaries. Conclusions. We can measure fossilized tooth. Mass spectra are very similar in fossil and recent samples. Differences related to growth of calcium hydroxide crystals we found in both teeth: calcium, oxygen, calcium hydroxide, phosphorus, soda, magnesium, and carbon. Consolidation of calcium and magnesium in clusters is observed. The result of our study is, and please keep in mind, the intermetallic layer of the shark tooth seemed to be very resistant against material exchange over decades of million years. Further analysis want to check deeper richness of the aqueous tooth, the DAM team. Thank you for your attention.
Okay, thank you, Klaus. Let's move to our next post-print. Michelle Karam. I'm not sure if this is the first author of the poster.
Hello.
Yes, we can hear you.
Okay.
Okay, we can see you now.
Okay. For my poster, I prepared a small presentation that I will be sharing now. Okay. So here.
Yes, we can see you.
I'm a first-year student, a PhD student at a GPM group. And so I will start about talking about the terahertz or the terahertz assisted atom probe tomography. As we know, in laser assisted atom probe tomography, the sample is evaporated atom by atom by the combined actions of a high DC field and an ultra-short laser pulse. However, this mechanism suffers from low spatial and chemical resolution, as shown in the following graphic. By using an IR laser having a wavelength of 800 nanometer, we can see the tail and the aluminium plus mass spectrum. Or by replacing this laser with a monocycle terahertz, we can see how the peak's width has reduced, and so how the resolution was improved. However, this thin peaks shows an asymmetric behavior, hence the need to study the flight dynamics of ions under the action of a variable electric field on a very short time scale that is less than 1 picosecond. And so for this purpose, we've started our studies with some simulations work. When at first we did a geometric modeling for the atom probe, following a symmetry evolution according to the x-axis with characteristics that are similar of the experimental one, and then we used the following equation to apply the terahertz pulse to the sample, and we changed the amplitude, and then we changed the frequency and the phases. And by solving the Laplace equation, we were able to simulate the electric field at the apex of the sample. And as shown in the following picture. And then we simulate the trajectory of the ions for variable starting time during the terahertz pulse, and we were able to collect the coordinate the position of the ion from the departure till the arriving to the detector. We were able to collect the coordinate, the velocity, time of flight, and the electric field. And here, to avoid the error in distance, we have fixed the ions emission from the sample of the apex, from the sample apex to the from the apex. And so the trajectory simulation has been released on the optical axis of the instrument. And then by collecting the data, and here's an example just from the results we got from collecting the data, and using the following equation, we were able to determine the evolution of kinetic energy for different type of ions. For example, here we can see how the kinetic energy that the lighter ion undergoes evolute. For lighter ions, we can notice how the evolution follow the shape of the potential energy, and this behavior that can be explained by the fact that light ions leave the intense field zone quickly, so they experience a small fraction of the terahertz, and then for the for heavier ions, this energy curve, or the quantity of the kinetic energy acquired by the ions is we can see a damping in the curve of the kinetic energy. This is a sample of the results we got from our work, and for the results, I've put them all in my in the poster here. Sorry for screens. Okay. I don't know if shown. I show here how oh, no screen.
No, it's the wrong screen.
Oh, okay. Here. Here.
It's show the screen.
Oh, okay. I'm sorry. I'm sorry. No, I'm okay. Here I show how the work we've did it by using the simulation. Here's for different. We show how for different or the behavior of the ion for different amplitude, for different frequency, for different phase, and then we compared our work with using an experimental terahertz pulse, and to try to find the best fit between the amplitude that we tested, and finally we showed how for different type of ion, for light ion, for heavier ion, how the mass spectrum get or how the resolution in mass spectrum or time of flight spectrum in this case got improved for heavier ions. And yeah, that's it. Thank you for your attention.
Okay, thank you. Thank you. Let's move to the next postprint.
Okay.
Are you there?
Yeah. Hello. Good morning. Can I speak? Am I audible?
Yes. Yeah, we can see you now.
Okay. Let me share my presentation.
Okay.
So can you see my poster?
Yes.
So good morning to one and all, or whatever it is. So my title of the poster is Effect of Terahertz Pulse Polarity on Mass Resolution of Terahertz Atom Probe Tomography. So there are different ways of evaporating a tip in atom probe tomography. So terahertz is one of the techniques to one of the radiation which falls in between the far IR and the microwave radiation of the electromagnetic spectrum. So generally, there are different ways of evaporating the tip. So for example, we can evaporate the tip by using electrical pulses, by using laser pulses. But in case of the laser pulses or the electrical pulses, what happens? The tip suffers the local heating. So the evaporation process is majorly associated with the thermionic emission or thermal effects are there. So to that results the poor mass resolution as shown by one of the previous speakers, Michelle. So in order to avoid that, Angela Vella et al. Developed a recent technique with using the terahertz pulses. The evaporation is being carried out. So the specialty or the uniqueness of this terahertz pulses is the evaporation will be completely associated with the pure electric field associated with the electromagnetic radiation. So for that, we have developed a experimental setup for generating of the terahertz setup. So let me zoom it for you. Yep. So this is the experimental terahertz setup. So we have using a femtosecond laser, which is split into two parts as the pump and the probe. So the pump is passed to a second harmonic crystal called beta-barium borate, BBO. So we generate a plasma. This is the plasma acts as a terahertz source here. The source is collected from the parabolic mirror, the terahertz, and we filter out the unconverted terahertz with help of a silicon filter. Then what we end up with a pure terahertz radiation. Rates will be sent to the atom probe for evaporation of the tip. So the recording of the temporal pulses, temporal profile is carried out using the electro-optic sampling. So if you see here, this is a typical terahertz temporal profile. So then we use the aluminum tips for evaporating the, as a sample to evaporate the using that terahertz pulses. But what we have done by changing the phase between the fundamental and the second harmonic of the pulse in the plasma, we can produce different kind of terahertz pulses. Like if you see here, in this graph, you have more positive polarity is there. In the second graph, you can see that it is a kind of the bipolar with the negative lead. So the negative part is leading here. If you see this is the positive part. So we are tuning the electric pulse associated with the terahertz by changing the polarity, by changing the phase between the fundamental and second harmonic of the laser. So these are the corresponding mass spectrum obtained with evaporating of this kind of the pulses. And if you see this with the positive, this is the operating voltages for different polarities. So for the positive polarity terahertz pulses, you see they are operating at very, very low applied DC voltage, and these are the corresponding aluminum plus peak with different polarity. So if you see that the terahertz pulses associated with the positive polarity are giving the better mass resolution, and the tail associated with whatever is not appeared in case of this. And the same thing we compared with the IR sources also at the same voltage. And if you see this, the tail with IR, you can see this. There is a tail, and when the same results are compared with the terahertz positive polarity, and the mass resolution is pretty good, and we get a better mass resolution. So this is the hydrogen peaks compared the thing. So in order to conclude the experimental setup for the evaporating with terahertz pulses, it has been developed, and various temporal pulses of terahertz temporal profiles have been produced, and these pulses are used for evaporating, and the pulses terahertz pulses with the positive polarity are giving better mass resolution and a better spectrum compared to IR pulses. So this opens a new channel for the terahertz community to evaporate the tips with pure electrical pulses, rather with in order to avoid the heating effects associated with IR lasers. And we thankful to the financial support for the Normandy, Europe, and Haiti board. Thank you. Hello. I'm done.
We can hear you.
Yeah.
Oh, I may start.
I'm done with my.
吴老师，吴老师。
I think the chair is frozen.
Maybe he lost his connection.
Yeah.
Okay, so I guess I should start. I'm the next one. Yeah. Yeah. Okay. I start share my screen. Okay. Hello, everyone. My name is Jianshu Zheng from the University of Stuttgart in Germany. My poster would like to propose a new methods to extract the Gibbs free energy from the local concentration fluctuations via a frequency distribution analysis on the simulated atom probe data. The theory is that we first define a new variable here as the relative variance, which is the variance of the number of a specific species scaled with its count, and by time averaging the entire system, we get the relative variance is has the relationship with the curvature of the Gibbs free energy curve, or the second derivative of this Gibbs free energy curve. But in the subsystem, when we would like to evaluate the local concentration, then we need to consider also the elastic of the small system with its surrounding region. Yeah. So with the elastic work term here, then we can have a correction from a large system to the subsystem. Okay. We know the Gibbs free energy curvature already, and then with help of the pure components known from the database, then we can do a twice integration, and then we can recover the Gibbs free energy curve. But how to get concentration fluctuations? Yeah, here we would like to use the atom probe. So in present work, we first use molecular dynamic to create nickel, copper nickel, and then evaporate it in Tapsin, and then reconstruct with the point projection algorithm and conducted frequency analysis to get the local concentration fluctuations, which is that for every single atom in this volume, we choose its nearest n atoms and evaluate within this volume the concentration of the second species and the distribution of the concentration. We can get the local composition distributions, local concentration fluctuations. Yeah. Okay. So we came to the result. Here I plot the relative variance versus n, which is the sphere size, or the n to the power of -1/3, which is proportional to the surface to volume ratio. We can see that this the relative variance has a size dependence, but nevertheless, we found a linear regime here, and with its extrapolation to the sufficiently or infinitely large n, that we can get the relative variance of the subsystem, which is the brown curve here. Yeah. And after that, we can say that if we get this already, then we can do this process and recover this curve. And also, we have compared these two averaging, time averaging and spatial averaging. They are quite similar, and we can use spatial relative variance for the representative of the concentration fluctuation. But when we applied it to the atom probe, we need to consider the effects of the limited detector efficiency. And here we derive the relation that says the extrapolating intercepts after applying the detector efficiency is the weighted average of the binomial distribution and physical distribution. So here we apply these methods onto the tip before the field evaporation. We can see that we take detector efficiency as 1.0 as a reference, and the model and the simulation work fits the models very well in the intercepts. Yeah. And then we come to after the field evaporation. Here we also take the 1.0 as reference. We can see that now after the field evaporation and reconstruction, this one has the -7.7% of deviation from the one before Tapsin, before evaporation. Yeah, but we assume that this is due to the difference between the copper and nickel in the reconstruction, and it's the reconstruction error. But we will expect it will be much smaller in other compositions. And here we can see still that the model of this one applying this detector efficiency fits quite well. It's even less than 1.4%. Yeah. So getting this one for different efficiency, then we can get the Gibbs free energy curvature, and then we can integrate twice to get the Gibbs free energy. Yeah. For this one, we would like to say that okay, it's fast, and we can apply this one to for every single composition, and even of the time of the temperature that above the let's say the Gibbs above the critical temperature allowed in the phase diagram. And of course, we need to apply more simulation concentrations so that we can recover the whole curve. Yeah, and we would like to later on apply it to the experimental data. Yeah, thank you all. Sorry that I skipped many details, but I would like to get your questions, suggestions, or even corrections afterwards. Thank you very much.
Okay, thank you, Jiansu.
Yeah.
Let's move to the next participant. Jen, are you there?
Yes.
Okay.
So you can see my screen, right?
Not yet.
Now maybe.
Oh yeah, now we can see.
Yeah. Okay. So thank you for giving me an opportunity to present my work here in the conference. I'm a postdoc working at Max Planck Institute for Ice and Fusion in the theory department, and together with Betty Sko from the experiment department. So just what I would like to show you today is ab initio field evaporation of in dilute alloys. We all know that atom probe tomography is a really nice technique which can basically give us spatially resolved chemical information in 3 dimensions. However, we often have this challenge that in APT, the spatial resolution is often limited. And the underlying phenomena, which is field evaporation, this electric field induced removal of atoms, is a atomic phenomenon which has quantum effects into it. And to take into account all this information which happens during field evaporation, we do DFT simulations. Right. So in order to be able to do DFT simulations on realistic specimen conditions, what we do is basically have a tool to generate slabs with certain steps and kink sizes instead of flat surfaces. And then to these high Miller index slabs, basically we apply electric field using generalized dipole correction, which is implemented in Sphinx, which is a DFT tool. And all of this is put into our pi iron IDE, right? So once we have the slab and once we have applied an electric field, what I do is I pick the highest atom and then move it along the z-axis that is away from the slab. And as I am moving it, I calculate the energy of the configuration. And I do so for different electric fields and for basically different heights of the evaporating atom. So for example, now I have looked at platinum evaporation from a 111 type of surface, and also a platinum evaporation from a 100 type of surface. And what we see here is that from a 111 type of surface, once I evaporate, so this is the barrier for the evaporation. And as we increase the electric field, the barrier for evaporation drops down. And the difference already in platinum is that when we evaporate from a 111, the potential energy surface seen by the evaporating atom is different compared to when it is evaporating from a 100 type surface, which is slightly more open. And even within 100 type surface, what we see is that at higher electric fields, there is sort of an appearance of a minima, which I thought was a minima. But later, if I just zoom it out, and you see that at higher electric fields near here, the minima is more open or more clearly visible. And in order to understand what was happening here, I put the atoms at these heights so that I could basically fill out more points in this region. Right. So when I do so, what I realize is that this is not actually a minima, but it has actually a splitting of potential energy surfaces. And this happens because the evaporating atom, for example, if it follows this higher energy, a slightly higher energy path, then what happens is it leaves the surface normally, more or less. Right? That is what we expect during our evaporation behavior. Whereas if it evaporates, if it takes the lower energy path, then what happens is it pulls out one of the step atoms, thereby also, and then rolls on top of it. And even further, there is even more splitting of the energies path, where basically the evaporating atom not only pulls out the terrace atom, it also pulls in the step atom. So the evaporating atom has not only destroyed its own starting
1 minute left.
Yeah, starting position, but also the other positions for the other atoms. Then I looked at rhodium evaporation also from both from rhodium surface and also from platinum surface. And I did the similar exercise. And what we see is that here I have plotted the barriers as a function of the electric field. And this is the critical field for evaporation. What we see is that rhodium to evaporate from rhodium requires higher field, whereas when it wants to evaporate from platinum, it requires lower field. So this is again in contrast to what the electric fields which we take based on pure materials. Obviously, that wouldn't be correct that in this case, which is showed here. So the idea here is to be able to propose possible alternate reconstruction parameter based on these kind of calculations. So with that, I'll thank you for your attention.
Okay, thank you, Sam. Let's move to our next participant, Christopher Freisold. Okay, Christopher. please.
Thank you very much. I hope you can see my poster. This is about the theoretical investigation of field evaporation near aluminum grain boundaries. And the motivation was more or less given by Francois yesterday, where he showed that the typical atom probe data sets contain more information than just the positions and chemical identity of the ions, but even the mass spectrum details can provide additional information. I'm very much intrigued by this idea of getting more out of the existing data sets. Now, what he showed for aluminum grain boundary is that if you look very carefully, you can see that in a situation where the sigma-3 grain boundary actually can be seen both in the positions, but also in these tails of the evaporation behavior, that they nicely stick out, and you can basically identify the position of the grain boundary without even knowing where the atoms really are with the atomic resolution. And the question here was whether, first of all, we can understand why this is the case, and secondly, what is the mechanism behind. And for this, we use DFT calculations, very much similar to what Cerium has just presented. So we basically calculate these kind of evaporation curves by pulling out single atoms for different applied fields, and then you see that there is a systematic trend of lowering the barrier, and so we can plot also the barriers as a function of electric field. Now we do this for situations which are as close to the experimental situation as possible. So we are looking specifically at stepped and kinked surfaces because this is where we believe most of the evaporation takes place. And one of the recurring features is what we call the rollover pathways, where atoms that are sitting close to the step edge actually do not move out of the surface in a vertical way, but they tend to move in between one or two neighboring atoms, rolling towards the step edge. Sometimes they even provide here a stable position and then leave from there, because then they're exposed to larger fields. So the critical barrier usually is this first step rolling over halfway or entirely onto the steps. Now, of course, we have to model this for grain boundaries, and it was quite tricky to actually come up with a model that would allow this. So we used the standard technology here, creating supercell models of both the grain boundaries and then cutting out of this grain boundary model a slab that would allow us to also simulate its surfaces. And then we use a slight miscut of this common 1-1-1 facet of these two grains to produce these stepped and kinked surfaces. Now, the interesting thing is, if you look on top view, you have different positions here. I've marked here with red the grain boundaries, and you see various possible evaporation sites. They're not all at the same height, so they basically will desorb one after the other. The interesting thing is that this rollover path differs significantly between the grain boundaries, where this is basically rolling along the grain boundary, whereas these atoms sitting within the grain have a different path. This path is aligned slightly different with respect to the evaporation fields, and hence the impact of the field strength on the barrier is different for the different sites. And this is plotted here in this central graph here, where you see these black lines, which are all the in-grain barriers, very similar behavior, and then the grain paths clearly stick out. This red curve here is this atom sitting at this grain boundary here, which actually has a much steeper slope compared to the others. But we also see in some cases the opposite. Due to the miscut, the grain boundaries are no longer equivalent, and there you see actually a flatter slope. In addition to these differences from the grain boundaries, we also see that there is a significant impact of the neighboring atoms. So if we
half a minute left.
Yeah, I'm almost done. Yeah, so nearby atoms, exposed atoms, will have an influence also on the evaporation barriers, even if they have not absorbed. And this means that the different evaporation behavior at the grain boundary will also influence nearby atoms, modifying their evaporation behavior. Yeah, that's basically what I wanted to show you. And if you're more interested, I'm happy to answer any questions via email or via chat or whatever. Thank you.
Okay, thank you, Christopher. Let's move to our last poster print. Martina Heller, are you there?
Hi guys, can you hear me?
Yes, yes, we can hear you.
Hi. So I'm happy to present now my, at the last one. Maybe I also put this. Yes. Okay. So I'm going to tell or to show you what we've done in our group about visualization of atom probe tips. So actually, we've seen a lot of nice research today, but in general, all of you have done nice images of your research, and visualization is always a key factor in the communication of your science. And you can see here on the left side, really nice gamma prime microstructure of a nickel-based super alloy. But yeah, this image is nice, but I think we could do better. On the right side, you can see nice images where you also have like big, nice atoms and also small ones. And these are done already with Atom Blend 1. That's maybe the older guys of you know in the older days. And with few first Blender versions, you were able to use it. But right now, with the new Blender version, it's not possible. So actually right now, what shall you do, or what can you do if you want to have a nice visualization of your atom probe data? You can use Atom Blend 2. So actually, for the new ones here in our community, what is Atom Blend 2? So Atom Blend 2 is a Python-based add-on for Blender. Blender is a huge open source software for 3D object visualization, modeling, and also animation. And the modeling animation part is really useful for us. So maybe I invite you now to lean back and see the video. I'm so sorry. Now I can start it. So lean back and enjoy this nice simulation of the gamma prime nickel-based super alloy. You can change the angle of the camera. You can zoom out, you can zoom in, and you see here nicely the precipitates on the sides, and in the middle, the other phase. So that's something what you can do with our tool. And what do you need for using our tool? So actually, you just need to have the POS or EPOS file and the range file from your atom probe tip, and then you have to use Blender, obviously, with the add-on, and you get out a JPEG or a video. So you use, or you are able to use the complete visualization possibilities in Blender. And the basics of our add-on is that you use a custom hardware accelerated renderer. So you can really render really fast, large data sets. And you can render also with, or the basic is that you render with shaders. They are running on our GPU. You can download our Atom add-on on GitHub from Peter Pfalfer. It's also open source, so it's cost you nothing. It's for everybody free to use. After you install it, you see this interface in Blender, and then you can load in here your EPOS file and the range file. You can change here the point size of the single displayed atoms. You can also change the amount of displayed atoms, and you can change the color of your elements. You can change if the elements shall be displayed or not. And you can also change here the amount of the single ions that you are going to display or not. You also can change the camera position, and then at the end, you just render your picture or render your video. So yeah, at the end, just go try it out, enjoy the image of your an image or a video of your science. And yeah, if you have any questions or recommendations, what we also shall implement, then just give me a mail. You can write me. And special thanks to Juliane. She's a HEVI student and she has all done the Python programming stuff. So thank you.
Thank you, Martina. So now we have all of your posters. Thank you for thanks all the poster printers and the speakers in this session. Thank you for your interesting talk and the wonderful posters. I'm sorry we are a little bit behind the time schedule. Now it's time to go to have supper or lunch or go to sleep. And so it's time to say bye-bye and see you tomorrow. Bye-bye.
Bye-bye. Bye-bye.